So, 可以吗 ？OK。Okay. We understand the projector doesn't work, okay, but the department, the TA is asking the department to help, to resolve this issue, but I think it's already like 10 minutes like into our class, so I think we can start. At least I can go over the syllabus, okay, and see like if the department can lend a helping hand, like after we finish the syllabus, okay. 好 ，OK， 好 ，OK。So, okay, first, this course is introduction to Bayesian data analysis, okay? Just want to make sure everybody is in the right class, okay? So I'm the instructor for this class, okay? My name is Minter Sang. You can call me Minter, Peter, Professor Sang, Dr. Sang, anyone works for me, okay? I'm fine with that, okay? And you see, on the syllabus, I list my office to be B213, okay? Sorry, okay. 对啊，拍谁？麻烦你了。就，对啊。
你的线是这条。
换
好了吗？
换了好几个，换了3条，事实上，3条都不 work， 我觉得很奇怪。我这边已经镜像输出了，这边这个输出是这边吗？已经是镜像输出了。
遥控器的。
遥控器，对。他那边就写关闭。我觉得很奇怪。
你的那个转换器有问题。
我们换的另外一台电脑也是不行哎。
也是这样的。
对，我们换了2台电脑，3条线，所以不得已才麻烦黄先生来看一下，实在是。If there is a traffic stopping snowstorm in Indianapolis next New Year Day, okay? Gamble B's, you get $100 if you draw a red marble from a stack of marbles with 5 red and 5 white marbles. So, which one will you pick? Do you pick Gamble A or Gamble B? Maybe I ask you, okay, you need to, invest maybe $10. Just like you buy lottery, right? So you have to, give away certain money for a probability to get big payment, right? But anyway, okay, so you have 2 choices, either gamble A or gamble B, okay, in this case. You get, if you get $100, if Indianapolis, will have like a traffic stopping snowstorm next New Year Day, okay, or okay, you want to gamble with the second option. If you drawing a red marble from a stack of marbles with 5 red and 5 white marbles. If you say, okay, I want to choose gamble A, what does that mean? That means, okay, your belief, that there is a traffic stopping snowstorm in Indianapolis next New Year Day. Okay, that belief, the probability is higher than 0.5, right? That is why you choose that, right? Okay? But if you say, okay, I choose the gamble B, that means your belief that there's a traffic stopping snowstorm in Indianapolis next New Year Day. The probability is lower than 0.5, right? So by using this trick, you are able to compare, you are able to identify your belief, okay? I mean, put it in probability, is larger, is higher or lower than 0.5, right? Okay, and then, okay, if it's if it's lower than 0.5, say you pick like you draw the gamble B in the first set, then you know your probability of like the gamble, your belief is lower than 0.5, and then let's try set 2. Okay, you get $100 if there's a traffic stopping snowstorm in Indianapolis next New Year Day. Okay, this is gamble A again. And gamble C becomes, you get $100 if you draw a red marble from a set of marbles with 1 red and 9 white marbles. You know, like a gamble C, the chance of winning for gamble C is 0.1, right? Right? Because you have 10 marbles, and only one of them is red, and the chance to pick a red marble out of this 10 marble is 0.1, right? Obviously, right? So now, okay, when I ask you to choose one from these 2 options, I'm asking you to compare your belief with the probability 0.1, right? If you choose A, that means your belief is higher than 0.1. If you choose C, that means your belief is lower than 0.1, right? Okay, so what I'm showing you here is a process of calibration. Okay, even though we are talking about this mushy, intuitive belief, okay, we are still able to sort of assigning a probability to this belief. Okay? By taking advantage of the human nature, gambling. Okay? So this is just to tell you, okay, why we can consider belief just like a regular probability, because you can do this like calibration. Okay? Yeah, it's already 10 o'clock. Let's take 10 minutes break. When we come back, we will continue. Okay? Sorry. So for coin flips, okay, the sample space is head and tail, right? Okay, so that's relatively easy, okay, because it's discrete, okay, because it's discrete. But how about, okay, the situation, okay, like, okay, American woman, okay, the average height of American women. Okay. Actually, most of the, I mean, I used to be in like Midwest, okay, Indiana and Ohio State, and then I spent 6 years like in Alabama, okay, which is considered the southeast of the U.S., okay, as a professor there. So actually from my observation, okay, like the American woman, okay, on average is not so tall, okay. It's well, I probably a little bit taller than Taiwanese woman, okay, but but not a lot, not a lot. But of course that's based on my own observation, okay, because I do understand like if you go to like a north part of the U.S., okay, the people there are actually taller. Okay, I don't know why. Okay, but the people, for example, living in like Minnesota or like Wisconsin, okay, people living there are, I mean, they are taller on average. Okay, so so because I don't have like a experience living in that area, so I don't know. But so we might believe the average American woman is 5'4". Okay, 5'4" is like 大概多少？大概164、165公分吧。Okay, like about 164 centimeters. Okay, something like that. Okay, I think like a lot of the Taiwanese women are taller than that, right? So, but anyway, like that's the we may believe that, okay, but what is the sample space here? Because we are talking about the height, right? So it could be 5'4", it could be 5'3", it could be 5'3.5", it could be because it's a continuous space, right? It's a continuous sample space. So there will be too many possible outcomes in this sample space. So, in the previous example, like a coin flip, because we have only 2 outcomes, so we can describe the probability of those 2 outcomes by a very easy, like for example, like a histogram. Okay, because there are only 2 possible value, 2 possible like outcome. So for each outcome, you have 1 probability. That's it. But for this one, okay, because we have infinite number of sample space, so we may instead describe the degree of belief by a bell-shaped curve. That because we believe like it's 5'4", right? So the highest, this bell-shaped curve is highest at 5'4", and it drops off symmetrically above and below that 5'4". Okay, so this actually is just like normal distribution. Okay, you can change the width and the center of the curve until it seems to best capture your subjective belief, because different person has different belief, as I say that. Okay, as I keep saying that. So normal distribution, okay, a probability whether it's outside the head or inside the head, okay, is just a way of assigning numbers to a set of mutually exclusive possibilities. But so now we need to talk about probability, right? We need to talk about probability. So for a probability distribution, okay, for something that has to become a probability distribution, something that has become a probability, okay, to describe a certain event, okay, then the probability needs to satisfy the following three properties. Okay, this is very important. Okay, the first one, a probability value must be non-negative. You can never have lower than 0 probability value. So you could have 0 probability, you could have positive probability, but no negative probability. The second, the sum of probabilities across all events, okay, in the entire sample space must be 1, okay, because once you consider all the possibilities, okay, you add them up, the probability must be 1, okay. The third one, for any two mutually exclusive events, okay, be careful, they have to be mutually exclusive events. When A happens, B cannot happen. When B happens, A cannot be there, okay. So if there are two mutually exclusive events, the probability that one or the other occurs, okay, is the sum of their individual probabilities. So this third one is also very important, okay. So these three properties together, okay, if something satisfies all these three probabilities, we can say it's a probability distribution, okay, of an event, okay, something like that, okay. So it could be discrete, it could be continuous, okay. So, for discrete situation, it's very easy to describe, but for continuous events, so it's more difficult. But for even if it's a continuous outcome space, we can discretize the space into finite set of mutually exclusive and exhaustive bins. Okay, for example, the x-axis denote the height. Okay, and the y-axis denote the number of person, and we try to we collect the data. We try to collect like the sample here is 10,000. Okay, we have 10,000 American women. Okay, their heights. Okay, we get the data set from these 10,000 American women, their height, and we put their height on this. Here, each point represent one woman in this data set, okay, and you can see that, okay, it's very dense in the center, and much you have much lower number of women on the two sides of this distribution. Okay, and here, okay, we try to discretize. Okay, in the sense that each bin, okay, we try to consider like 2 inches as wide as one bin. Okay, so for example, 55. Okay, this bin is 53 to 55. This bin is 51 to 53, and this is 55 to 57, and so on. Okay, so we divide this continuous sample space into some number of bins. This is we discretize the continuous event, continuous sample space into discrete like outcomes. So each bin, okay, will consist of like the height in between these two numbers. Okay. So once you put discretize this space into the finite set of mutually exclusive bins, then you can, sort of like use a histogram to describe all these women, okay, their height, okay, in this, histogram, okay, and then you can divide, okay, originally, okay, you can put down like, okay, I mean the y-axis originally could be number of women, okay, with that fall into a certain beings. But once you divide the number of women that, that fall into certain beings with the number of samples, what you have is this probability density here. Okay? So in particular, number of measurements that fall within the interval 63 inches to 65 inches is 1,473, okay? Which means that the estimated probability of falling in that interval is 1473 divided by 10,000. It's 0.1473. So it's, well, he's talking about 63 to 65, right? So this one. So this is actually referring to, okay, this actually referring to probability mass. Okay, probability mass. Okay, this one referring to probability mass. Okay, number of occurrences divided by the total number of the instances. Okay, in a certain being, but because it's a continuous outcome space. Okay, so we can another way to divide this is that, okay, for example, we can divide like each beam as 1 inch, okay, in width. Okay, if you do that, then obviously, okay, you can see it's going to be, you have more number of beams, and the probability mass will look very similar, but it's going to be, what should I say? Like it's going to be the granularity is going to be much thinner. Okay, it's going to be the resolution is going to be much better. Okay, but it's obviously like both this one and this one, they both look like a bell shape, right? And also, if you say, okay, what I want to consider, originally I will talk about probability mass, but you can also talk about probability here. Where is it? Okay. No. I think this one. Okay. The probability mass, for probability mass, we know like it satisfies all those 3 requirements. Okay, like the first one, for each beam, the probability mass, like the result is greater or equal to 0, right? And also, if you add up all the event points, across all the bins, okay, it's going to be equivalent to the denominator, the total number of events. So the probability add up will, across all the bins will be 1. And the third one, okay, for 2 different bins, the chance for a height that fall into either one of them is the sum of these 2 bins, because each bin is mutually, these bins are mutually exclusive. Okay, so probability mass, okay, is a probability density. It's a probability distribution. Okay, but another way to describe that is, probability. You can divide the probability mass with the bin width. Okay, that's called the probability density. Okay, so for example, okay, originally like this one, when you divide the probability mass with the bin, which is in this case is bin width is 2, so it's going to be 0.074. But once you divide this one with bin width, okay, because bin width is 1, so it's going to be 0.066, okay, and you can easily do a very simple and a quick observation that probability density is also a probability distribution. Okay, it also satisfies those 3 properties. But one thing very, very interesting is that, okay, let's consider another case. Okay, in this case, we also have like 10,000 samples. Okay, 10,000 randomly selected doors that are manufactured to be 7 feet tall. Okay, so we go to stores to purchase door. Okay, that are supposed to be 7 feet tall. Okay, and then we measure the height of the door. Okay, you can imagine because originally when we measure the height of American women, okay, the average height obviously is not. It's going to be the height of the American women is going to be distributed much widely, right? But now, if you consider the doors that are manufactured to be 7 feet tall, and you measure it, obviously, because it is manufactured to be 7 feet tall, so the height must be close to 7 feet, right? Okay, actually, it's if you look at it, what is 7 feet, by the way? 7 feet in inch. It's 12 times 7, right? 84, right? Right? You know the conversion between inch and the feet, right? Each feet is 12 inch. So when we say 7 feet, each foot is 7 inch. So when you say 7 feet tall, that's 84 inches. So if you can look at that, 84 inches obviously has the most number of, of course it is still continuous space. We're still doing this discretization, okay? But now, okay, this bin width is much narrower because obviously, this door height are very close to 7 feet anyway. Okay, so bin width is actually 0.025. Okay, 0.025 inch. The difference is, each bin width is very narrow. But you still see like most of the population, okay, will be close to 84 inches. That's obviously, okay. But you can see like, also some manufacturers are doing a very poor job, right? So because you can even see some occasion like it is like a 83.6 inch. You can see one occasion in here. That's actually 0.4 inches difference. 0.4 inches is more than 1 centimeter. Okay, that's considered a lot. Okay, when it comes to door manufacturing. Okay, same thing goes for like the other end. Okay, here it's close to 84.4. So again, it's a more than 1 centimeter difference. Then the specification, because specification is 7 feet tall. Okay, so we have 10,000 doors and their heights are here. Okay, and when you calculate, okay, one interesting thing is, obviously you can calculate probability mass, and for each probability mass, for the probability mass for each beam is again, okay, greater or equal to 0. But when it comes to probability density, okay, remember I say, when it comes to probability density, because you need to divide the probability mass with the beam width. So for example, if you divide the probability mass with beam width for this particular example, okay, you will get 2.829. So you say, wait a moment, this is a probability, right? How come probability can be greater than 1? This one is greater than 1, not to mention the other. This part, they are all greater than 1, by the way. Okay? But that's okay. Why? Because if we check out these 3 requirements for probability density, does it ever mention that any probability distribution, like a reading of a probability, for a certain situation cannot exceed 1? It doesn't say that, right? These 3 properties does not say anything about a probability cannot be greater than 1. Okay, even though it may be against your intuition. Okay, I just want you guys to understand. Okay, for probability mass, because it's defined by the number of occurrences divided by number of total samples, okay, for any beam. So the probability mass can never exceed 1. But for probability density, it's different thing, okay, because you have to further divide the probability mass by the width of the beam. So it could be greater than 1, okay? So, well, the probability mass of the ith interval, okay, is denoted as this, okay? And we know the sum of this is 1, okay? And we know, like, for example, okay, if we do, this is probability density, right? This is probability density. And the sum of the delta x times this probability density, okay, will also be 1, okay, which can be described like this. By the way, the book, okay, the Doing Bayesian Data Analysis book, the author obviously is not in mathematics department, because this dx, okay, in math department, they normally put it at the end, right? It should be integral px dx. Okay, but that author likes to put the dx, in the front. I just want you guys to understand this is, integral px dx. Okay, not integral dx px. I mean, well, but you get the idea. Okay, so because this one looks more like that. Okay, so well, just to want you guys to understand that. So the integral of the probability density is still going to be 1, regardless. So probability density obviously is a probability distribution. Okay. So when this delta x is is getting smaller and smaller, okay, we normally do not consider probability mass. We normally consider probability density. Okay, or you can consider that as a continuous case. Okay, so for the most famous probability density function that has been used, okay, is normal distribution, or another way to call it is Gaussian distribution. Okay, it looks like this. It's a bell shape. Okay, the mathematical formula, it looks like this. Okay, the important parameter for this distribution, are the mean, okay, which is denoted as mu, and the standard deviation, which is denoted as sigma. Okay, and the mu determine where the center is located. Okay, and the sigma determine how wide this bell shape looks like. Okay, so we define a random variable x by writing stats.norm, okay, mu sigma, okay. This because we are talking about normal distribution. Okay, this is SciPy, by the way. Okay, so we can get an instance x from this using RVS, okay, random variable method. Okay, so in the example below, okay, we ask for 3 values: mu equal to 0, sigma equal to 1. This is the standard normal distribution that we usually talk about, like with mean 0 and the standard deviation 1. Okay, and then we create the random variable x, this capital X, okay, by using the mu and the sigma, and then we try to get 3 samples from this distribution, okay, and put them in lowercase x. So, so common notation in statistics, okay, to indicate that a variable is distributed as normal distribution, okay, with parameter mu and the sigma is like this. X, okay, this small delta, you can say this. You can translate this small delta as like is distributed as. Okay, so when this n obviously refer to normal distribution with parameter mu and sigma. So you can translate this formula as x is distributed as normal distribution with mu average and standard deviation sigma. Okay. So then, okay, we weighted each possible outcomes by the probability that it happens. So this procedure defines the mean of a probability distribution. Okay, we call it, another way to call the mean is expected value, okay, which can be written as E of EX. Okay, So it's basically it's defined as like a px times x and summation. Of course, in this is discrete form. Like if it's continuous, then it's a like a px x dx. Okay. Again, let me remind you, this dx should be put like at the back. Okay. So that's like a expected value or mean. Okay. I mean in statistics. Okay. So here, okay, we can consider the probability density function px equal to 6x 1 minus x, and which is defined over the interval x in the range of 0, 1. And you can compute the ex, okay, like this. Okay, so I will not go into the detail. This is a very simple integration anyway, right? So the result is 0.5. But one thing I would like to ask you is that, okay, before you calculate this average, the first thing you should calculate is that, actually, is whether or not this density function really is a probability distribution. Okay? If I ask you, is this a probability distribution? What should you check? Remember those three properties? The first one, in between 0 and 1, is this density function always positive or 0? Yes, right? Yes, right? Okay. The second one, the third one, like mutually exclusive, like the probability add up to be the event for those two, like this is obviously true, but the second one needs to be verified, right? Okay. In other words, the first thing you should verify is perhaps this is oh, sorry, there's a 6. The first one you should verify is this one. Okay, this is the second property, remember? Okay, you have to ensure this is a probability distribution. Okay, and then you can try to calculate the average of this distribution. Okay, like this. Okay, but I think this is also very easy. I will not go into detail, but if you have trouble doing this integral, let me know. It's still early. We can drop this class, okay? Because this is really freshman calculus or high school calculus. Well, you should have learned that, okay? But if you already forget everything, that's fine. That's fine. I mean, it's just like you can take some other classes. This class is probably not for you. Okay. So just want you to understand, how do you verify a density function is a density function, is a probability density function. Okay. And then, how to calculate the expected value from a probability distribution. Okay. Okay. So, by the way, I mean, some students ask me like, okay, in the homework and exam, am I going to assign like a computational type of question? Yeah, that's possible. For example, something like this. But I suppose the computation doesn't, as long as you have the concept, it should be relatively easy, right? Okay, it should be relatively easy. So, the variance, okay, of a probability distribution, okay, really can be defined as like the square difference between x and the mean. So it's if you write it in like formula, it's going to be something like that. So px times x minus ex squared, and you integrate that over all the x range. Okay, so that's a bar x. Actually, for the probability distribution, this one will lead to standard deviation. Okay, and obviously this one can have a discrete version as well. I will not go into detail. This is very simple. Okay, how do you compute this? How do you, convert this one into a discrete version? You can do that yourself. So in normal distribution, about 34% of the distribution lies between mu and the mu plus sigma. Okay, so in other words, if it's in between mu minus sigma to mu plus sigma, okay, within these two sigma range, okay, you have 68% of the data in this range, or you can say it's close to 70%. Okay, because if you talk to like Americans, they normally like treat the number very inaccurately. So 68% they will say, oh, it's about 70%. But you get the idea, okay? Yeah, the majority of the instances fall in between mu minus sigma to mu plus sigma. Okay, so this gives you a rule of thumb. Like if you want to consider the majority range, like what range you should consider. Okay, but this is only good for normal distribution, and it may not work well for the other distribution. Okay, so do not overgeneralize this fact to the other distributions. Okay, but I would say that, okay, a lot of distributions, if you if you try to do what we say about like a convolution, okay, you try to add a lot of like distribution together, eventually it's going to approximate a normal distribution. Okay, so if it's like a very complicated situation, a lot of time you can use a normal distribution to approximate that like very well. Okay, so normal distribution is actually like very convenient, and that's also why it is the distribution that has been used the most. Okay. So the probability can be interpreted, either as how much a value could be sampled from a generative process, okay, or as how much credibility the value has relative to other values. So you can see the first explanation is more frequentist approach. The second explanation is more Bayesian approach. Okay, but they are somewhat like similar anyway. Okay, because we already talked about this credibility, okay, or belief, okay, you can actually calibrate that anyway, right? So, okay, when p of theta represent the probability value of theta instead of the probability of sampling theta, then the mean of p of theta can be thought of as a value of theta that represents a typical credible value. So the mean will become the most credible value. Okay, the standard deviation of theta, which measures how wide the distribution is, okay, can be thought of as a measure of uncertainty across credible candidate value. So how uncertain you have for your belief, because remember the belief, okay, the most credible or most the best way to describe your belief is the mean, right? Okay, but how uncertain, is your belief? Can be measured by the standard deviation. Okay, if the standard deviation is large, then it means you do not believe that so well. Okay, but if you believe that very, very much, then the standard deviation value should be small. Okay, so just to give you some idea. Okay, so it doesn't matter what the value of mu is, because mu just means the center location. Okay, but the important thing is the sigma. Okay, you can see the difference between. Of course, for this 9 figure, okay, the column have the same mu with same sigma with different mu. The row, okay, the figures in a row has the same mu, but with a different sigma. Okay, you can see mu control where the center is located, and the sigma control how wide the distribution is. When the distribution becomes wider, the height, the highest point is also reduced. Okay, highest points will also become lower, because the integral of this will be 1 anyway, right? Okay, so when it's wider, obviously if you want the integral to be the same value, then the height of mean will be reduced. And in this discussion, I have never mentioned that the value of any point here, okay, is greater than 1 or not. It doesn't matter, right? It doesn't matter, as I have shown you by that door example. Okay, because we are talking about probability density function here. So some of these values, okay, could be greater than 1, but that's fine. That's fine. Okay, it's okay for probability density function to be greater than 1 at some point. That's not a problem. Okay, so let's it's already 55. Let's take 10 minutes break. When we come back, we will discuss this joint probability. Okay. Okay, so, let's consider the probability, with two different factors, two different factors. So, which is a conjunction of two outcomes. So, for example, the probability of being dealt a card that is both a queen and a heart. Okay, so there are two possible outcomes. Okay, and but this is easy, right? Because the card has only 52 outcomes, and the queen, the rank of a card, and the type of cards, are relatively fixed. So that's the simple case. Let's consider a more complicated case. Okay, so this is like the proportions of combinations of hair color and eye color. Okay, and we consider black, brunette, red, and brown hair color. For eye color, we consider brown, blue, hazel, and green. Okay, so this is actually a data collected in 1974, okay, by social scientists, okay, and obviously this data was collected in Western country, okay, because you can see that, there are more people in brunette, red, and brown than people in black hair. Okay, and also, for example, for eye color, you may wonder how come we don't have a black eye? Okay, but okay, what is our eye color? For Asian people, what is our eye color? Black? No. Okay. In Chinese we always say, "黑眼珠," okay, black eyeball, okay, black eye. But anyway, in reality, actually, if you check the literature, okay, they will say we Asian people have brown eye. Okay, 棕色眼睛. If you look at the mirror, you will see you have a brown eye. Actually, it's scary to consider somebody has the eye color is black, totally black. They looks like a ghost, Okay, actually, okay, if you use the term black eye, that has different meaning in English. So, what does that mean by black eye? Okay, well, a little bit of English here, okay? So if somebody punch you in your face and you have you are black here, that's, we normally call that black eye. Okay, so we are never black eye, okay? Don't use black eye to describe your eye color to Western people, because they will think, oh, you are just beaten by somebody? So be careful, okay? But anyway, okay, we Asian people have brown eyes, okay, not black eyes, by the way, okay? So anyway, here we consider hair color and eye colors, okay? So this shows the proportion for the population, okay? I believe, well, it doesn't, does it say anything about, yeah, it doesn't say the whole, the whole population in this study, okay, it doesn't show here. But at least here, it shows the proportion of the people with different hair color and eye color, okay, combined hair color and eye color, okay. So, so this is obviously much more complicated than the car example, right? Poker card example, because poker card, well, everything is fixed, but here it's much more complicated. So in each cell, the table indicates the joint probability. Okay, because we are going to use this example to talk about some important concepts. So the first one is joint probability. Okay, of particular combinations of eye color and hair color, obviously. Okay, so if you have two outcomes, their joint probability, okay, we can consider their joint probability. And we may be interested in the probabilities of the eye colors overall collapse across hair colors. Okay, so these probabilities are indicated in the right margin of the table. Okay, so therefore we call them marginal probability. So, so for example, we consider, for example, like a brown eye color across different hair colors. Okay, so you can see it's going to be displayed here. Okay, basically this one is like the summation of all these numbers, which is displayed here at the margin of the table. So it is why it is called marginal probability. Okay, so in this study, okay, 37% of the people have brown eyes. Okay, and 36% of people have like blue eyes. 16% of people have hazel eyes, and 11% of people have green eyes. So of course, if you add them up, it's going to be 1. Same thing, okay, if you consider, for example, black hair across different eye color, then 18% of the people have black hair, okay, and so on, okay. So this one is also a marginal probability, okay, and obviously, if you add up all these numbers, it's also 1. So, we have. So, if attributes are discrete, in this case, okay, in the case that we just discussed, like the hair color and the eye color, they are discrete, right? So the PE, okay, probability of certain eye color is the summation of the PEH. This PEH is like we consider all the joint probability with this eye color, across different hair colors. In this case, the hair colors, different hair colors are considered, and we add up all the joint probability to get the marginal probability of this particular eye color. Okay, the same thing can be said for hair color. The probability of a certain hair color, okay, is something like this. So if attributes are continuous, then we need to change this PR equal to this one. PRC DC, okay, I'm sorry, this DC should be put at the end. And the PC should be integral PRC DR, where DR should be put at the end. You get the idea, okay? Shouldn't be too difficult to understand, right? Okay? So, the probability of one outcome, given that we know another outcome is true, is called conditional probability, right? Previously we just keep saying conditional probability, but we didn't really give the formula for that, right? Okay, I keep telling you we are going to use conditional probability. We are going to use Bayesian Bayes rule, but Bayes rule obviously is for conditional probability. But now it's a good time to talk about conditional probability. For example, conditional on that the person has blue eyes. The probability that the person has brown hair. What is the probability the person has brown hair? So total amount of blue eye people is 36%, 0.36. Blue eyes. Okay, the marginal probability is 36, 0.36. Okay, 36% of the population has blue eyes. And among these 36%, okay, we want to see what is the probability or what is the portion of the people to have brown hair. So the people to have brown hair, out of these 36%, 0.16, okay, in this 0.36, okay, have brown hair. Okay, so the conditional probability is going to be 0.16 divided by 0.36 is going to be 45%. So 45% has brown hair, okay, given that the person has blue eyes. So this is very important. Why? Okay, because, okay, if you don't know, if you do not know anything, okay, remember the example I just mentioned, what is the probability that it's cloudy here in Zhongli? And then I said, what is the probability that if it's sunny, what is the probability that it's clouded? We talked about this, remember, at the beginning of the class today, right? Okay, so, okay, same thing. The general probability of having brown hair is 0.21 here. If you only consider, okay, if you, at random, you pick up anyone, okay, the chance for that person to have brown hair is 21%, right? 0.21. But once you realize that that person has blue eyes, once you realize that person has blue eyes, the chance, okay, the chance of that person to have brown hair, okay, increases to 0.45, right? To increase from 0.21 to 0.45, this is relocation of probability, right? Right? So this is Bayesian inference. This is Bayesian inference. Okay. The thing that here, okay, we do everything by calculation, right? We obtain everything by calculation, right? From that table, okay, we get that 0.45, we get that 0.21, we get that 0. All these numbers are obtained from the computations, right? So now, okay, this relocation of credibility, okay, can be done mathematically, okay? So let's consider this computation of conditional probability, okay? The notation of conditional probability is PH over E, right? Given a particular eye color, the chance of that a particular hair color, okay? Okay, this one is PHE stands for PEH, the joint probability, divided by P of E, right? Right? Hopefully, this is, and from the PE previous discussion, we know, okay, the PE can be written like this, right? Summation H PEH, right? Okay, in high school, when you learn Bayes rule, okay, this is the Bayes rule. Okay, but and this shows the conditional probability of, for example, if you know that person has blue eye, what is the chance for that person to have black hair is 0.08. The chance for that person to have brunette hair is 0.39. The chance for that person to have red hair is 0.08. And the chance for that person to have blonde hair is 0.45. So you can do all this conditional probability. Given blue eye, okay, is like that. And the chance for, blue eye, given a blue eye person, okay, the chance for all different hair colors obviously is 1, right? Which is the sum of all this conditional probability. That's obviously the case, right? And you see here, basically this one, the denominator, okay, for example, if we want to remember, originally we are discussing this one, right? The 0.16 is a joint probability, and 0.36 is the marginal probability that that person has blue eye, right? Okay, which is this one. Okay? And if the attributes are discrete, that's what we have. Okay? We just discussed that. When the attributes are continuous, then we need to change our formula into this one. The only difference is that this one is this denominator. Okay? Where, this DC should be put at the back, but you get the idea. Okay? So it's important to recognize that in general, PR on condition of C is not equal to PC on condition of R, because you can obviously write the formula. The numerator will be the same. Both are joint probability PRC. The issue is the denominator. The denominator will be different. Right? Right? Okay. So when we say the probability of X given Y, we do not mean that Y has already happened and X has yet to happen. This has not, this doesn't mean the causality. Okay, if you say Y has already happened, and what is the probability for X to happen? This is more like we are describing a causality, like kind of like a chance that Y causing X. Okay, but no. Okay, all it means is just that we are restricting our calculations of probability to particular subset of possible outcomes. Okay, so a better growth of Px on condition Y is a better description is among all joint outcomes with value Y, the probability of them, also has the value X. Okay? So this is a better description. It has nothing to do with causality. Oh, by the way, if you guys are interested in causality, there's a book that is very famous. I would really recommend you guys reading. Okay, it's the book. The title of the book is called "The Book of Why." I don't know if you have heard of this book, "The Book of Why." Okay, the author is first. The Book of Why is not what should I say? It's more like for popular, for regular population. It's not for just for engineer or for somebody who has to master mathematics. No. It's more like for general population. It is a science book for sure. Okay, but it's more like a popular science book. Okay, The Book of Why. I mean, the author is actually a Turing Award winner. Okay, Julia Peer. Okay, he actually derived like all the causality theory. Okay, and because of that contribution, he won the Turing Award about 20 years ago. Okay, he's a professor at the computer science professor at the UCLA. Okay, very very famous, and I believe you can find translation of that book. Okay, from bookstore as well. I do think that book also help you to understand some AI knowledge, because you can also use causality theory to explain AI. Okay, so that book is a very very good book. Okay, I highly recommend. Okay, anyway, but the Bayesian is not necessary about causality. Okay, Bayesian is much older. Okay, because it comes from statistics. So let's consider this example. This example is a more complete example. Okay, consider trying to diagnose a rare disease. Okay, rare disease. Okay, suppose that in the general population, the probability of having the disease is only 1 in 1,000. Okay, so probability of a person having disease is 0.001, right? 0.001. Okay, because 1 in 1,000. So we denote the true presence or absence of the disease as a value of parameter theta. So we say theta equal to this crying face if the disease is present in a person. So the first sentence, okay, actually means right? In other words, obviously, the probability for a person not having disease is what? 0.999, right? Get it? Okay. So, where is it? Okay. So, the base rate of the disease is therefore, this one is, okay, I already wrote it. This is our prior belief that a person selected at the random has the disease. Okay, so suppose that there is a test for the disease. Okay, so remember we are in a COVID-19 era, right? So we know test kit, a rapid test kit, very very well, right? A lot of you may already tried it many times anyway. Okay, so anyway, so this test kit has a 99% hit rate. What is 99% hit rate? 99% hit rate means if a person has the disease, then the test result is positive 99% of the time. This is pretty good, okay? Actually, the COVID-19 test kit that we have, I don't think they have the hit rate is so high. So let's use let's say the test positive. Let's just use a plus sign to indicate positive. Okay, so that means what? The probability if somebody has the disease and the test result is positive. Okay, so on the condition that person already has the disease, the conditional probability, okay, that person tests positive is the 0.99, right? Right? So it's going to be something like that, right? This one. Okay? And also, that we know that the test has a false positive rate of 5%. What is false positive rate? So it means when the person is healthy, if the person is healthy, the test result may show he has a disease. That's a false alarm, right? So in the condition, under the condition that the person is healthy, the result come up positive under this condition is 5%, right? So 0.05. Right? So it's this one. Okay? So our question is, suppose we sample a person at random from the population, we just randomly get somebody and run the test on that person, okay, administer the test, and it comes up positive. What is the posterior probability that the person has disease? So we are looking for the probability of this one. P, okay, now we know that person is positive, right? So we know that result is positive. What is the probability that person really has disease, right? We want to know on the condition the test result is positive. Okay, that person really, under this condition, that person really has the disease. What is the probability? We want to know this one. Right? So based on this, can you compute this one? Okay. Actually, you could do, what you can do is that you can construct a table, something similar to this one, something similar to this one, but in a much easier format, because okay, one side indicate the person has that particular rare disease or not. The other side indicate that person tests positive or not. So each side you only have like two possible outcome. So the table only has like a four joint probabilities, right? Okay, so let's do we? Yeah. Okay. So it's something like this. Well, this one is running out of ink. So And we also have marginal probability. So this one indicate a test. This one indicate the illness or disease. Okay. So we have like a happy face. We have like a crying face. And this one is a positive, negative. Okay? And first, we know like from the first one, okay, we know this one is the marginal probability is 0.001, right? And this one is 0.999, right? Right? And then, okay, if this one is 0.99, okay, this one is what? What is this one? This one is like this one is P crying face and the P positive and crying face, right? Joint probability of this, right? So based on, because we already know the crying face, right? P crying face, we already know that, right? This is 0.001, right? So based on 0.001 and the 0.99, we can get this joint probability, right? Right? This is a plus and a crying face. Plus and the crying face. So this one, we get this one. Okay? So if you get this one, you also get this one, right? Because 0.001 minus this one is this one, right? Okay, so we get this one. And then look at here. This one, what is this one? This one is probability of happy face as a denominator, and the probability of plus and the happy face, right? The joint probability of plus and happy face as a denominator. And we already know the probability of happy face, right? Which is 0.999, right? And if you know this one, then you know the joint probability of plus and the happy face. So plus and happy face. So you know this one, right? If you know this one, and because we already know this, the marginal probability, this one, so we know this one as well. So if you know these two, you can compute this one, right? Right? So it shouldn't be too difficult, right? Right? So actually, it's exactly just like what I said, okay? You can compute this one. You can compute, yeah. You can compute all these things. And then after that, after you do that, okay, you try to compute this one. This one. This is the one that we are interested in. This is what? This is probability of plus. Okay. On top is probabilities of plus and crying face. The joint probability of plus and the crying face. So probability of plus is here, this one. And the probability, this is denominator. And probability of plus and crime phase is this one. This is your denominator. This is your numerator. Okay, so it's going to be this one divide. Is it? Am I? No, yeah, I think I draw the column and the row differently than this one, but you get the idea. Okay, you get the idea. So the answer is 0.019. So let me repeat. Remember I just told you that this rapid test kit is pretty darn good, right? Because, well, just like our description, okay, this rapid test kit, okay, the hit rate is 99%, and the false alarm rate is 5%. This is pretty good, okay? I don't think any COVID-19 rapid test kit is as good as this one, okay? So, even with this such a good rapid test kit, okay, and if you try to use it on a person at random, and when it comes up positive, the chance for that person to have disease is only, well, close to 2%. That's very low, right? That's very low, right? You may feel it's against your intuition. You say, oh, this person tests positive. How come the chance for that person to have that disease is only like less than 2%? Why? There are a few things I can describe. I can discuss with you here. Okay. The first thing is like this. Okay. What is the person to have disease at random? What is the probability that a person has disease at random? The person to have disease at random is this one, right? 1 out of 1,000 people, right? So the original probability is 0.001. Now the probability becomes 0.019. The difference is how much? The probability increased 19 times, right? From this situation, from the chance that person at random to have a disease. It's already 19 times higher. So yeah, that test kit works. That test kit works. But the issue is that, okay, because this is a rare disease. Okay, this is a rare disease. So if it's a rare disease, I mean, well, I mean, it's just not going to, have like a the chance for, even if that person tests positive, it's just not going to be very likely that person has disease. It's just like increase that probability. So normally, okay, when you have this test kit, okay, in mathematics, in like a medical field, okay, how do they use this rapid test kit? They normally actually only use rapid test kit in 2 situations. Okay, the first situation is that, okay, well, the disease is rare, okay, but you already have certain symptoms of that disease. And then we try to use the rapid test kit on you to see, okay, if that's the case. Okay, so the person is not a random person. That person already has certain symptoms from that disease. Okay, let me use a COVID-19. But COVID-19 is probably not a good example now because COVID-19 is no longer a rare disease, right? Okay. Okay. Let me use the AI AIDS. Okay, AIDS. I'm not against like a homosex. Okay, first time disclaimer. Okay, I'm just talking about like a particular disease. Okay, by the way, AIDS can be spread like even across like gender. Anyway, so anyway, AIDS is still considered rare disease, right? I mean, but if somebody already exhibit certain symptom from, of the AIDS, for example, like because AIDS is the disease that you are gradually losing the defense to the attack of the outside like bacteria. So if the doctors think, well, this guy is very easy to get infected by many issues, so the doctor will start to suspect that this person may have AIDS. So in that case, the chance for that person to have the AIDS is no longer 0.001. The chance for that person to have the AIDS may be like 0.01. Okay, maybe 1/100. Okay, or even like maybe 1 over like 2 out of 100 maybe. So when the doctor used the test kit over, okay, with such a capability over that patient and it come up positive, well, then the chance, say original is 2%, is 0.02. Now, okay, this probably will be increased by 19 times. So it become what? 38%. Well, now the test kit is very helpful, right? Right? Because when the test kit showed up positive, yeah, it's close to like 40% that this person has that disease, right? So that's the first thing. Okay, the first situation that the doctor has to observe, certain symptoms and then use the test kit. Another situation is what? Is the situation when, like COVID-19, it's no longer a rare disease. For example, in Taiwan, like COVID-19, I think it's maybe 30 to 40%, okay, of population that already carry like a COVID-19, virus. So in that case, the rapid test kit helps. Of course, even the rapid test kit is not as effective as the one that we described here. If it can increase the probability by twice, then as I said, if it's like 10%, okay, then increase by maybe twice, then it's 20%. So it's still quite useful, right? And this also answered one question. Remember, a few years, not few years, I think probably a little bit more than a year ago, right? When Taiwan doesn't have so many COVID-19 cases. Remember, in legislation 院，在立法院, okay, some people just keep asking the government to run a big test over a large area to see what is to find out all the people who have COVID-19. But at that time, in Taiwan, COVID-19 is considered a rare disease, right? Okay, so based on this, you can understand. Okay, even if we have a very effective rapid test kit, okay, the chance for somebody who really doesn't have disease, but the test positive, and it's actually very high, right? Okay, I mean, the you know, when it tests like a positive and that person really have the disease, it's only 2%. And not to mention, like, I mean, in other words, when the test come out positive, that person doesn't have disease, it's 98%. Okay, so you want to, you know, put all these people in quarantine? Okay, that sounds like a strange, right? So that's the reason, that's the rationale why the government agency doesn't want to do that back to like probably more than a year ago. Okay, so the situation now is different, but the situation because now the COVID-19 is no longer a rare disease. So this example, I just want to use this example to show you, okay, the concept of Bayesian inference, and it happened to have a connection to our, what should I say, to the COVID-19, which is like the disease that we are facing, like nowadays. Okay. So I guess we're running out of time today. So we'll stop here today. Okay. So next time we'll start from like here. Okay. Any question? If no question, let's call it a day. Okay. I will see you guys next week. Okay. I think I will. So so we talked about the joint probability, and we talked about conditional probability, as well as an interesting example last time on vaccination, right? Not vaccination, like a rapid test kit. Okay, rapid test kit. And so today we are going to continue this topic, but before that, okay, just want to remind you, okay, I have uploaded the homework 1 to the class, to the E class already, right? Okay, please don't download it and work on it. But in addition to that, there's one moment. I believe. This one. There's so before we continue the lecture, okay, just want to show you this thing. There's a EMI. Okay. there's an EMI questionnaire that the school has to collect. This one, okay. The first one is what you guys need to answer, okay. The short URL is here. The QR code is here, okay. I understand that. I mean, this is, you guys may not, if I don't give you some motivation, you guys may not answer this questionnaire, okay? So I will include this one in homework 1 as a bonus question, okay, for 20 points, okay, 20 points. So, yeah, I mean, I will have the student upload this to E-class for you guys, okay? Whoever answer this one, okay, before the deadline, okay, I believe deadline is maybe about a week into March, so we still have about a week, okay, to do this questionnaire, okay? So you should have plenty of time to finish this questionnaire, okay? This is just for the EMI purpose, okay? So anyway, yeah, I mean, you don't have to take photos, anything like that. I mean, because I'm going to post this on E-class. It's just, yeah, you can just take time to get this done. Oops. So that's, well, can be considered like bonus for the homework 1. Okay. So let's go back to where we left off last time. Okay. So one interesting that you may observe, like from the example that we the rapid test key example, is that, okay, what we are given is something like this, okay, on the condition of sad phase, okay, on the condition of the sad phase, and the the true the positive, like a probability of positive, and the condition of the happy phase, the probability of the positive, okay. You see on the condition here, on the condition of either happy phase and a sad phase. The happy phase and sad phase are used as the condition side of this probability, right? Okay, but what we are asking at the end, okay, what happened in the condition is the positive and the, well, it's a sad phase, but you get the idea. The phase expression, okay, is no longer appear in the condition part. It appear in the other side, right? Somewhat like these two fields are somewhat like switched, right? Okay, so the previous one and this one, okay, this switching is actually much more important than you may think, okay? So, well, Where is it? Okay, here. When the row variable represents data value and the column variable represents parameter value, remember what I told you? Okay, if you have a model, that model has parameters. Remember? And that parameter sort of control that model. Okay, if you still remember, I gave an example like Gaussian distribution. Okay, the variable that control Gaussian distribution is the mean and the standard deviation, right? So there are many mathematical models, okay, that have like parameters, okay. So think about this. If one dimension, okay, let's consider this joint probability. Okay, joint probability has 2 dimensions, right? Okay, if one of the dimensions represent data value, okay, and then the other dimension, okay, represent the parameter for the model, then what happens is like this, okay. You are given, this is what you are given certain parameters, okay, because your model, original, you already have the model. So given certain parameters of that model, and the probability of those, of the data you collected, okay, when this entry, okay, these entries are given. And also, you have the prior. The prior is actually the probability distribution of the model parameters. Okay, so these 2 things are given. This is we also have this in the rapid test kit example. I just forgot to mention. Okay, here, where is it? Okay, there's a test for disease. That disease is, sorry, not that one. This one. This is a rare disease. Remember, we talked about rare disease. The rare disease, the probability of the rare disease, okay, because that disease, okay, can be found like 1 out of 1,000, right? 1 out of 1,000. So the probability of the sad phase, okay, without any condition, probability of the sad phase is 0.001. Remember? That's we are given this one, right? This is 1 out of 1,000, right? As well as this, it's here. Yeah, we are given this one. We are given this one. We are given this one, right? So this is probability distribution of the parameter value, okay? Of course, this is a simple case because this is really not a distribution. This is really like we are given this probability of prior value already. But because this is like a real, more like a discrete case. So it's relatively easy. But okay, you can imagine this is like the probability distribution of the parameter value is given. Okay, so it's like what I mentioned. Okay, so you have this one. You have this one, and what we are interested is to compute, okay, on condition of the data value, on the condition of the given, of the collected data value, what is the probability distribution of the parameter values? See, these two things switched, right? So what happens like this, okay? So okay, you believe in something like remember like okay, you know when for example like you believe in like the weather, okay? The weather is in Zhongli, okay? Remember we talked about the cloudy example, okay? If your prior is like okay, it's represent like the chance that Zhongli is clouded, okay, is maybe 40%, but okay, so that's this one. That's this one. This is your prior. Okay. And now you collect the data. Okay. The data is well, maybe you see like somebody tell you it's raining, right? Okay. So this is the based on the current parameter setting. But of course, in this example, the parameter the Zhongli has 40% of the cloudy weather. It's not really has not played any like a role in like you collect data like wow somebody tell you it's raining. I mean the chance of the cloudy, okay, from the prior, okay, it doesn't affect the probability of the the thing you collected, like it's raining. But based on this value, okay, you know it's raining. You have to adjust your parameter value, your belief in parameter value accordingly, right? Remember I told you the chance may be 90% raining, right? I mean, it's no longer 40%. It's based on the observed data. So this is exactly the inference. Okay, this inference is based on, it's originated from the prior and it's based on the data, because the data, you are conditioning the new belief based on the data that you collected. Okay, so this is the the Bayesian inference, the most important aspect of the Bayesian inference, and this is why how the Bayes rule, is applied here. Okay, so if you draw a table, it's going to look something like this. On one dimension, you have the data value. On the other dimension, you have a model value. Okay, and it's obviously a joint probability, and you can also have your marginal probability as well. Okay, and then you are given certain value from this table, and you are asked, as I said, for the opposite, I shouldn't say opposite, like the conditional probability, but now it's like it's conditioned on the data. Original is conditioned on the parameter. Okay, so if you feel like, this looks strange, don't worry, because I'm going to give you a more concrete example shortly, okay? But before that, let me, remind you, okay, the base rule, okay, the base rule. The term, okay, the technical term we use in the base rule, okay, okay, if you know on condition of the theta, the probability of the D, okay, this term, okay, is called likelihood. And the P of theta is normally what we call prior. Okay? And this one multiplied by this one is going to be the joint probability of D and the theta, right? Based on the base rule you learned from the high school, right? And if you divide that thing with the P of D, okay, the probability of the theta, that's called evidence. Okay, that you are going to get what we call posterior. Okay? So, for P of D, this evidence, okay, it can be represented by this thing, right? It's a marginal probability, so you can use you can try to calculate like each term separately and add them up. So this is obviously a discrete case, right? This is a discrete case. That's why we use summation here. Okay, but you get an idea. Okay, so once you know the likelihood, you know the prior, and you can calculate the P of D, the evidence, then you can get your posterior. Okay, which is like the probability or distribution of the model parameter, okay, on condition of the given of the collected data, okay. So this is on the one side, okay, on the right hand side, you only see like a certain D on condition of theta. On the other side, you see theta on condition of the D. This switching is much more important than you may think. Okay? Of course, if you have the discrete case, we also have the continuous case. Okay, so if the variables are continuous, then the marginal likelihood, okay, this marginal likelihood is this one. Okay, by the way, P of D. Okay, or evidence, whatever you call it. Okay, okay, you can replace this one into the, the integral. Okay, it's going to be something like this. But of course, this d theta should go, to the end of this formula. Okay, I again apologize for this sloppy notation, but you get the idea. Okay, you get the idea. So this whole thing, okay, is really not so complicated. Okay, the only thing that is difficult, okay, mathematically, is this formula. Okay, when you use the Bayesian data analysis to do inference, okay, a lot of time, okay, as I say, the likelihood and the prior are not so difficult to obtain. Actually, prior is more like a belief It's more like social agreeable result. Or even if you don't have that, okay, you can have a what we call vague prior, okay, just uniform distribution, meaning you don't say if the parameter range from 0 to 1, you just say, oh, it's a uniform distribution. You don't favor any particular value for that parameter, and then just let the Bayesian inference to tell you how it should distribute it, okay, how it should distribute, okay, to be more like trustworthy. But so as I say, likelihood priors are not so difficult to obtain. The difficult part is the evidence, because evidence, when it comes to the continuous case, I mean, it is integral. And well, just like most of you guys have learned from like calculus, the integration, okay, of a given function, okay, is could be very complicated, right? I mean, if you want to get a closed form result, okay, I mean, for differentiation, okay, for most of the time, if I give you a function, okay, you differentiate that function based on certain variable, and you can give me like a closed form. But if I give you, a very arbitrary like a function, even though the function could be simple, but the integration could take you, could be very painful, okay, to obtain. I mean, sometimes you cannot even do it. A lot of time you cannot even do it. It's just, well, that's the nature of the mathematics, unfortunately, okay? But so remember I told you, okay, traditional statistics was, I mean, has become very popular, like in the 1990, okay, sorry, 19th, I should say like early 20th century, okay, early 20th century. But the Bayesian data analysis wasn't get much attention, okay, wasn't getting much attention until late 20th century. Okay, why was that? The primary reason is because, okay, because Bayes' rule was there, okay, for 100 years, okay. It's not like a Bayes' rule was just invented like in the late 20th century. No, okay, it was there for a long period of time, but it's just like when people, even for mathematicians, when they saw this formula, they feel hopeless because they couldn't get the closed form, okay, for arbitrary function. Okay, but now, okay, because we have a computer, okay, a computer especially personal computer becomes so, easy to obtain, okay, in the late 20th century, okay, so that actually push the prosperity of the Bayesian data analysis. Okay. So a few terms to just to get out of the way. Okay. For example, what is the independence, okay, of variables? Okay. In general, when y has no influence on x, okay, then the probability of x given y, okay, is just probability of x. Okay, when you condition x on y, but because y has nothing to do, it doesn't affect x in any way. So, so P x on condition of y equal to Px for all values of x and y. If that's the case, then we say x and y are independent, okay? And also, okay, because Px on condition of y, we know that this can be written as Pxy joint probability of x and y, probability of x joint probability of x and y, divided by Py. So if you put this thing here, then it tells you that, okay, the joint probability of x and y will be Px times Py, okay, for all values of x and y, if, okay, x and y are independent, or if and only if, because these two things are, two ways, okay. So one interesting question, okay, are the eye color and the hair color independent? Remember the case, okay, we talked about, where is it? Here, this one. Is the eye color and the hair color, these two things, independent? Yes or no? Yes? Why yes? No, why no? If you want to say yes, you pretty much need to verify. Px y equal to Px Py. Okay, for all xy. So this, okay, if you have that, it tells you that x and y are independent. Okay, if you want to say, oh, they are not independent, then you only need one to give me one example that Pxy, the joint probability of x and y, is not the multiplication of them. Okay, for example, okay, because we are Asian people, right? So we have brown eye, black hair, right? And we know the probability of the joint probability of brown eye, black hair is 0.11. So 0.11, will there be, well, the probability of the eye equal to brown multiplied by the probability of the hair is black. The first term is the marginal probability. The brown eye is 0.37. So this is 0.37. This one is black hair. The marginal probability is 0.18. So these two multiplied together does not equal to 0.11, right? Right? So it tells you that the eye color and the hair color are not independent. They are dependent. Okay, as for dependent by how much, that's a different issue. Okay? That's a different issue. I mean, there are certain ways to measure how much dependency two variables are. But here we just want to answer, these two variables are independent or not. Okay, you can arbitrarily, pick another joint probability to verify. Okay, I'm not saying, I mean, you just need to have one entry that doesn't satisfy this formula. And you can refute the case that, I mean, these two variables are independent, okay? So go back to so many models assume that successive values of random variables are all sampled from the same distribution. Okay, the distribution remains the same. Now, every time you sample a value from this distribution, it does not affect this distribution. Okay, at least the distribution remains the same for the duration of your experiment. Okay, so those values are independent of each other. Okay, so this assumption, okay, in this assumption, we normally will say the variables are independently and identically distributed, or abbreviated as IID. Okay, they are IID variables. Okay, so this is like a technical term, okay, used in statistics very often. Okay, of course, this is not always the case. Okay, here, I mean, we have a non-IID variable. Okay, for example, okay, let's consider, okay, we try to sample the temperature, okay, from the atmosphere. Okay, oh, sorry. Yeah, the atmospheric CO2 measurements. Okay, because we know like CO2. Okay, if you look at CO2 distribution just for a short period of time, of course you can assume it doesn't. It is IID. But if you see that we are considering this experiment from 1959 to 1997, so obviously, okay, the CO2 distribution is not identical, right? Because we know, okay, the CO2 gets accumulated over time. That is why we have this 温室效应. I don't know the English term. The something house, right? But I forgot. Greenhouse effect, if I remember. Okay, greenhouse effect. Anyway, this is like how the CO2, okay, distribution gets like changed over time. Okay, and obviously you cannot assume this, for such a long experiment period of time, the CO2 distribution is IID. That's not the case. That's obviously not the case. Okay. But again, let me remind you, this is because the experiment, the period we are considering is quite long. Okay. You see the x coordinate, okay, represent the year. Okay, actually runs from 1955 to 2000. So it's almost half a decade, So in such a long period of time, like, a lot of things can change. But if you only consider this experiment for maybe like an hour, then you could assume this IID, right? For CO2 measurement, okay? you can consider it's IID. I mean, if it's only an hour. So it depends a lot on a lot of factors. Okay, it depends on how long you consider the experiment is. Okay, and also like a certain sample, like a process. Okay, but anyway, okay, in this class we assume the variables are IID. Okay, variables. Okay, so for the models that we consider, okay, models are simplified description of a given system or process, okay, that we are interested in. Okay, so this description normally is mathematics, and as I said, they have certain parameters to control them. Okay, so those descriptions are deliberately designed to capture only the most relevant aspect of the system, okay, and not to explain every minor detail. Okay, after all, okay, if you want to model something in mathematics, you have to simplify it. Okay, if you do not simplify in the model design, then you cannot have a model, or your model will be too complicated to work with. Okay, so remember, like you say, how about like a certain minor factors that we do not consider in the model design? That's fine. Remember, in this class, the model we are considering are probabilistic. Remember, and you can take that minor factor, okay, into account, okay, because the model is probabilistic. So those probabilistic, aspect can be considered as like the impact from those minor factors. Okay, so this is one reason a more complex model is not always better one, because it lacks explanation. It is not easy to work with. Okay, so there are many different kinds of models, obviously. So in this class, we'll restrict ourselves to Bayesian model. Okay, so here's the Bayesian modeling process. Okay, let's go over this quickly. Okay, we actually will, as I will say, I mean later. This is like this process may be, done, multiple times. It may be done. Maybe we may need to go through this process iteratively. Okay, given some data and some assumptions on how this data could have been generated. Okay, we design a model by combining building blocks. Okay, what are those building blocks? Okay, those building blocks are probability distributions. The most well-known one is, I already told you, the Gaussian distribution or normal distribution. Okay, and there are other distributions that you are going to see. I hope to be able to talk about the beta distribution today, but let's see. Okay, so most of the time, these models are crude approximation, just approximation. Okay, but most of the time, okay, this is good enough. Okay, good enough. And then we use Bayes' theorem, okay, to add data to our models, and then we derive the logical consequences. Okay, so that's the Bayesian inference. Okay, the first one is really like the model design. The second part is the Bayesian inference. Okay, so at the end, okay, we are conditioning the model on our data. So data becomes, in the Bayesian inference, eventually data will become like the condition. And the model parameters will be, we'll see the distribution for model parameter based on condition of the data. Okay, that's the second one. The third one is, then we need to, check, okay, check the model, okay, to see if it makes sense according to different criteria, okay, such as, the data, our expertise on the subject, okay, the understanding on the subject, if this is plausible, and sometimes by comparing several models. So this is like we need to be able to explain the result, okay, of the inference and make sure it is plausible, okay. So if it's good, great, okay. But we may need to go over them multiple times. Why? Because later on you may collect more data, right? You may collect more data. So you may need to go through the process multiple times. And also, if this result is not plausible, it is against the intuition, okay, or like against the knowledge on this subject, then what happens is that, okay, either the model, okay, design has some problem that you didn't take into account the important factor. Okay, I'm not saying the minor factor, I'm saying the important factors. Okay, either that's the case, or something's wrong. When you put those probability distribution together, something's wrong. So anyway, you may need to redesign your model, or the data collection could go wrong, right? The data collection, may be biased, okay? But anyway, okay, so you find out the problems, okay, and then redo the whole thing again. So this is, as I said, this is more like a iterate, even though this looks like 3 steps, but we need to, a lot of time need to go through them like iteratively. And it may be nonlinear. Why is it nonlinear? Because if the model works, okay, if you just collect more data, then you start from here, okay, and do this again. But if a model has problem, of course you need to go back to fix the model, okay, fix model design, and then do it again. So it depends on the situation. So that's why I say we say this is non-linear fashion. Okay. So Bayesian models are also known as probabilistic models, okay, because they are built using probabilities, okay. They are based, actually, the Bayesian models are based on probability distributions. So it will be, we will be talking about a lot of different distributions in this class, okay, at a later time, okay. So because probabilities are the correct mathematical tool to model uncertainty, well, we talked about that already. So let's take a walk through the garden of forking path, okay. So distribution. The prior distribution should reflect what we know about the value of it doesn't show up. The theta parameter, the theta, it's not showing up. There's a theta parameter, okay, before seeing the data, which is D, okay, capital D, okay, this is, I hate it. We are talking about this theta and the D. Okay, one dimension represents the theta for the model parameter. one-dimension model, the D, okay, the data, okay, D. So I'm talking about the theta and D here in this table. Okay. So if you know nothing, like Jon Snow, do you guys know Jon Snow? No? Okay, then you guys don't know the movie, the TV series. There's a TV series called what? The novel is called The Song of Ice and Fire. 冰与火之歌. I mean, when this novel becomes the TV series, it's like the Game of Thrones. Do you know this TV series? So this Jon Snow is actually one character in that story. Okay, because that guy came out of nowhere. Okay. So nobody knows his background, okay? So that's why the author of the textbook used this guy's name, okay? Just want to give you an idea, okay? That I mean, this guy, because it come out of nowhere, nobody knows his background, so that just like we know nothing, okay? And by the way, I mean that TV series is very famous. I think they won like some awards, and it's a very good TV series. Okay, so we could use flat pliers, just like uniform distribution, just like what I said. Okay, that basically means that you do not commit to a certain value during this. The only thing you know is okay. This theta, okay, has a certain, valid range. Maybe it is good, okay. It could be in between 0 and 1, so you just use a flat plier there, or it could be good from 0 to maybe 100, okay. Then again, in between these two extremes, you use a flat plier. Okay, so that's a very simple approach. Okay, use flat plier, and then okay, use the Bayesian inference, and it will give you the more plausible result. Okay, so in general we can do better than pliers, than the flat pliers, because sometimes we know something, know something better. For example. Remember, like the flip coin. Okay, if the flip coin comes from the government, you may say, okay, you believe this 90% of the time, right? So the theta that it will be fair. The theta, if the theta represents a fair coin, then this belief should be much higher, right? Maybe 90%, right? But if you get that coin from a magic shop, then, well, the belief that this coin is fair is much lower, maybe 10%, right? So something like that, okay? So you can come up with your own prior, okay? So the use of prior, okay, the use of priors in Bayesian data analysis is why some people still talk about Bayesian statistics as a subjective. They don't think Bayesian statistics is because Bayesian statistics talk about priors, and prior is about sometimes it's about like your own belief, obviously. Okay. So some people attack that, okay? But actually, such a prior is just an assumption, okay, that we made, okay, when modeling, okay. So just as subjective or objective as any other assumption, okay, such as likelihood, okay. Likelihood is actually a formula, okay, that we are going to talk about, okay. Likelihood is how we will introduce data in our analysis, okay. It's an expression of the probability of the data given the parameters. So if you have the parameter fixed, then the probability that you have such a data is the likelihood. Okay. I mean, when we describe the likelihood like that, it looks difficult, but in reality, it's actually much more easier than you may think. Okay, so in some texts, you will find people call this term sampling model, statistical model, or just model. But anyway, I mean, we just call it likelihood. I actually, I mean, checked like more than one textbook. Okay, doing patient data analysis and the book that we are using this for this semester, both of them call this likelihood. And the other books, I mean, well, it depends on how mathematics oriented those books are. I mean, if the book is more mathematics oriented, okay, then it may have call this sampling model, statistical model, you know, because but don't worry about that, okay, as long as, I mean, we understand what we are talking about, it should be fine, okay. So once we have likelihood, okay, then we could have our posterior, okay. The posterior distribution is a result of Bayesian analysis and which reflect all we know about a problem, okay, given the data in the model, obviously, okay. So posterior is a probability distribution for theta parameters in our model, okay. So it's a distribution. Okay, it's a distribution. In rapid test kit example, okay, it is a single value, okay, which is close to 2%. Remember, the reason for that is because it's a discrete case, but in almost all the case in Bayesian inference, okay, we are talking about distribution. Okay, we're not talking about a single value. Okay, so this distribution is a balance between prior and the likelihood. So the prior tell you one thing, likelihood tell you something else, and the resulting posterior is actually a compromise between these two. Okay. So there's a well-known joke, okay? A Bayesian is a guy, okay, who vaguely expecting a horse, okay? This expectation sort of describe a prior, okay? Okay? And then catching a glimpse of a donkey, okay? So this is the data the Bayesian guy, obtained, and then strongly believes he has seen a mule. Okay, so, well, that's the posterior. You guys know, you guys know horse, right? That's no problem, right? How about donkey and the mule? Horse is, I don't need to explain horse, right? Donkey is 驴啊，驴跟那个叫什么东西？那个怪物叫什么的？不是那个电影里面那只 Talking Donkey。Shrek， 对 Shrek。You guys seen the movie Shrek, right? The guy, the donkey, I mean, is the guy in that movie that keep talking, just cannot stop talking. Okay, so that's the donkey. Okay, which kind of like looks like a horse, right? Okay, the mule is有点像鹿啊 kind of like a big deer. Okay, mule actually also has 那个脚怎么讲？那个它是那种一片的。Okay, but I don't know how to, you know. But anyway, it's also kind of like you can say it's one kind of deer. Okay. So they look horse, donkey, mule. They are different animal, of course, but they look similar. So you can say mule is a compromise of a horse and the donkey. Okay, so this is like what Bayesian inference is doing. Okay, so this joke captures the idea of posterior being somewhat compromised between prior and the likelihood. Okay, so conceptually, okay, so we can think the posterior are the updated prior. Okay, once we have the data. Okay, so posterior from one analysis can be used as a prior of the new analysis. So this can be done iteratively. You get this posterior, and you can use this posterior as the prior for the next round of the inference. Okay, so this makes Bayesian analysis particularly suitable for analyzing data that becomes available in sequential order. Okay, because a lot of time we get data like in sequence anyway. Okay, so well, sorry, it's already 10:05. We're almost. Let's take 10 minutes break anyway. Okay, when we come back, we'll continue. We are almost done with the statistical part. Okay, and then we are going to talk about an example, which is much more down to earth. Okay. 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 Okay, so let's continue. Okay, so last term, okay, the marginal likelihood, okay, also known as evidence. Okay, so this, okay, is the probability of observing the data averaged over all possible values of the parameters can take. Okay, because it is not conditioned on certain parameters anyway. Okay, so for most of the class, okay, we will not care about the marginal likelihood, as we will think of it as a simple normalization factor. Okay, because eventually this evidence or marginal likelihood is going to be used to make sure the result is going to be a distribution. In other words, the integral, okay, part is going to be 1. Okay, so that's why, okay, this marginal likelihood is considered as a normalizing factor. Okay, so we can do this because when analyzing the posterior distribution, so we only care about the relative value of the parameters, not their absolute value, because this value, p theta on condition of y, okay, this y is actually just like d, okay, is proportional to the py on condition of d times P of D. Okay, so even though, okay, they are not the same, we know they are not the same. Okay, this one and this one, they are different by a P of D, right? Divided, or P of Y. Okay, I mean, because we use Y for D in this formula. But remember, P of D or P of Y is a fixed value here. Okay, it's a fixed value. So it doesn't, that's why we can say they are, they are proportional. This one is proportional to that one. Okay, because the denominator is a constant. Even though we don't know what that is, okay? And also, when you collect the data, I mean, sometimes the data comes in batches, right? So, do you consider the ordering of the data has impact to the result? I mean, the base rule gets us from a prior belief, P of theta, to a posterior belief, P of theta, on condition of D. So when we take into account some data, obviously, okay, but suppose we observe some more data, okay, so we denote that as D prime. So we can then update our belief again. So P of theta on condition of D to P of theta on condition of D prime and D. But the question is, does our final belief depend on whether we update with D first and D prime second, or update with D prime first and D second? So is the order of the data, okay, is it going to play any role in the inference? Okay, so this is hard to say. Okay, it depends. Okay, it depends on the model function that defines the likelihood. Okay, so in many models, the probability of data, okay, does not depend in any way on other data. So that's, the joint probability of P D prime on condition of theta, it will be the same as P of D on condition of theta times P of D prime on condition of theta. Normally, it's like that. So in other words, the data probabilities are independent. If you have this, then the order doesn't matter. Okay, the order doesn't matter. But it is not always the case. If the likelihood function has no dependencies on data ordering, then the posterior should not have any dependence on data ordering. So we can formally prove this, okay, because P of theta on condition of D prime D, we can write it like this, okay, and without changing the denominator becomes like this, because as we said, we have this, right? P D prime on condition of theta equal to this one. So we can break the denominator of this into this one. And we can break the numerator of this into this too as well. And then, okay, we can, reorder, because it's multiplication anyway, right? So we can change the order and then put them back to be like this. So P of theta on condition of D prime D is the same as P of theta on condition of D prime. If you have this, the joint probability of D prime on condition of theta equal to P of D on condition of theta times P of D prime on condition of theta. If that's the case, then the order doesn't matter, okay? But it's not always the case, okay? if you ask, like, do we have any, like example that the order matters? Okay, one quick example I can come up with is like, okay, yeah, well, for example, okay, if you put, I just put in some sugar in my coffee, like during the break, okay, if you use like a sugar cube, okay, and then you put the sugar cube into your the cup, okay, and the sugar dissolve, right? The sugar dissolve into the water, or well, coffee, whatever you say, okay. So the sugar, dissolve, okay. The rate of the sugar dissolve, okay, depends on the surface, how much surface it has in contact with the water, right? You see what I'm saying? Okay, because the sugar, okay, 那个跟那个溶解的速度跟表面积有关系嘛 ？Yeah, the how much area, okay, the sugar cube, okay, has contact with water, okay, somewhat like determine like how quickly the sugar dissolve into the water. So when it is a big cube, when it's a big cube, it has a larger surface, right? So when you first put your sugar cube into the coffee, okay, it dissolves quickly. Okay, but when it becomes smaller, if you do not stir it, 如果你不搅它的话 if you do not stir it, just put it there. Okay, the smaller sugar cube dissolve slower, right? Because it doesn't have, that much surface to get in touch with water, right? Okay, so basically, okay, so if you say like, okay, we put in a sugar and then, okay, let's measure like the sweetness, okay, the change of the sweetness of the water, okay, the first 10 seconds and the next 10 seconds, okay, this is dependent, right? This experiment is dependent, so the order matters. Okay, in some experiments, like the order matters. Okay, because it's this sampling. Okay, I mean when you do the experiment, I mean at this moment, okay, the sample you get here, it's something has changed. Okay, the cube, the rate of the cube dissolving, okay, obviously change. Okay, so well, I mean, it is not the order, okay, matters in this case. I mean, it's no longer independent. Yeah, I wanted to use like another example, but I kind of feel like it's not a good one to give, because like last weekend, I mean, my friend, we were drinking like a red wine and discussing like most famous like news recently, like you know in Hong Kong, you know 那个女生被分尸，然后那个 okay, so we were, I mean, of course we are jokingly discuss like what is the best way to kill somebody like without being caught, you know. So like we talk about like so our conclusion is like there's a case about more than 20 years ago, probably before you guys were born, okay, which was happened in Tsinghua University, inside the university. A female student killed his boyfriend. And then, okay, she was caught, okay, but I think her method is brilliant, okay, because she is into chemical engineering, chemical field. So what she did is like she used I don't know what the English term for that. You know, 王水. Okay, she used 王水 to dissolve the corpse. She is almost successful, but the corpse takes time to dissolve. So she, you know, before the job is completed, she was caught. Okay, so I kind of feel like if she really get the corpse dissolved, okay, that's what, you know, I mean, it's like a link to the dissolvation. This thing. I mean, anyway, like it's difficult to be caught. Okay, I mean because the corpse the corpse disappear, and then, you know, I mean, because she is doing experiment, right? So she get those like those material all the time, you know. So it's difficult to say, oh, you are. I mean, you may use this to dissolve corpse because she is into chemical department. She's a student in the chemical department. So it's so that thing is probably the most you know, the best way to kill somebody without being caught. I don't know, yeah, but anyway, yeah, probably we shouldn't discuss this in this class, right? Okay, so anyway, okay, so so it's time to talk about a more concrete example, even though this example is still discrete, okay. We still have to talk about discrete example because, as I said, like when it comes to integral, okay, because the continuous case always involve integral, and the integral is difficult to solve unless it's you are talking about conjugate prior. What is conjugate prior? We'll talk about that later. Okay, I mean, you can say conjugate prior is a particular type of prior that that we can solve the integral to get a closed form easily. Okay, that's called conjugate prior. Okay, but you know, for most of the case, I mean, the conjugate prior doesn't work anyway. Okay, unfortunately. So let's look at the discrete case first. Okay. So the coin flipping. Okay, this coin flipping problem or the beta binomial model. Okay, it's a beta binomial model because it's the distribution that we consider is a beta distribution, and the likelihood function is a binomial. Okay, binomial. Okay, so that's why we call it beta binomial model. So it's a classical problem in statistics, and it goes like this. Okay, we toss a coin a number of times, and record how many heads and the tails we get. Okay, based on this data. Okay, we try to answer the question. Okay, is the coin fair or not? or more generally, how biased is the coin? So this how biased is a coin, this bias, okay, biased has three meanings. Okay, and depending on the context, the meaning of the bias may be different. Okay, for example, okay, the first meaning is like what we use, like sometimes like I say, okay, you are biased. I say you are biased. I mean, because you may treat somebody better and treat somebody bad, right? So not fair. It's biased. Okay, so this is one first meaning. The second meaning is like okay, for example, how biased the coin. Okay, it actually refers to the probability of the coin flipped head. Okay, or more generally, okay, bias can be used as to refer to probability, a certain probability. Okay, so in this case, okay, it's like the probability that a coin is, coin flip. The probability coin flipped is head. Okay, the third one, I forgot the third one. Anyway, just want you to be aware. Okay, when we say how biased is the coin, I'm not saying the coin is unfair. Okay, because coin doesn't treat somebody unfair anyway, right? It's not a person. Just want you guys to be aware. Okay, so note about the terminology. When we refer to a bias, we will be referring to its underlying probability of coming up head. Yeah, I already. So when the coin is fair, it has a bias of 0.5. So other times, the term bias may be in curricular sense of departure from fairness, okay, as in head biased or tail biased. So this is more like unfair treatment, something like that. Okay, just want you to be aware. So you may ask, so why do we need to consider coin flipping? Coin flipping doesn't, we don't do coin flipping experiment anyway, right? So why do we consider that? Okay, because coin flips are a surrogate for myriad of other real life examples that we do care about. Okay, do you guys know surrogate? The term surrogate? You can say it's a 替代品. Okay, something similar. Okay, for a given type of heart surgery, we may want to know what is the probability that patients survive more than 1 year. Okay, if you define, okay, after a surgery, okay, the patient survive more than a year, okay, means successful. Okay, if after surgery the patient does not survive, okay, more than a year, as failure, then you can link the successful kind of like the coin flip, the head, and failure kind of like the tail, and this obviously like the surgery can be treated as a coin flip, right? Okay, so other cases like for survey question, we may want to know the probability of agree or disagree, right? So a question can be, if somebody answered a survey, for a particular question, the answer could be agree or disagree. Again, as long as the result is like a two-sided, okay, you have two like results that cannot coexist, then you can sort of link that event to a coin flip. Okay, or in a two-candidate election, okay, such as Donald Trump and Joe Biden, okay, before the election itself, we want to estimate from a pool. We may want to estimate the probability that candidate, well, maybe Trump, will win. Okay, again, this event is, has two possible outcomes. Okay, so you can treat each, pool estimate as one trial, like a coin flip. Okay, or studying arithmetic ability by measuring accuracy on a multi-item exam, okay, for which the item outcome are correct or wrong. Oh, by the way, okay, in English, okay, if you see multi-item exam or multi-choice exam, okay, then okay, the answer is either correct or wrong. Okay, there's no like partially correct case. Okay, because if you direct translate multiple choice exam, I mean, if you direct translate that into Chinese, it becomes 复选题, right? But if you are in high school, the 复选题 means like you can choose like multiple answers for one question, so you can get partial credit, right? Okay. But unfortunately, Americans are dumb. Okay, they are stupid. They never have that type of exam. Okay, their exam, if it's choice type of exam, okay, the multiple choice just refer to 单选题, single choice. Okay, it's just you have multiple options, but from those options you choose one answer. Okay, in U.S. that type of exam is referred to as multiple choice exam. Okay, there's 我们的复选题没有在美国没有在做这个的。There's no our multiple choice exam. I mean, doesn't exist. Okay, in U.S. Okay, so that's why. Okay, when we say multi-item exam or multiple choice exam, the result can only be correct or wrong. Okay, because there's no partially correct. Okay. So obviously, okay, for the first example, the heart surgery, obviously this type of question is important in medical field, right? Okay. For the second question, okay, this type of thing is important to social scientists, right? Because social science, I mean, do survey all the time. Okay. For the third question, okay, for political science, I mean, they care about this type of question. For the last question, okay, if you are into education field, or if you come from the fourth floor, okay, 那个就是那个网学所 okay, then this one is important to you guys. So you can see that for different areas, you can easily find like questions that are somewhat like similar to coin flips. So that's why the coin flips is a good example to start with. Okay. So the first thing we will do is generalize the concept of bias. So we will say that a coin with a bias of 1 always land heads, okay? And the bias of 0, okay, will always land tails, okay? And the one with the bias of 0.5 will land half of the time heads and half of the time tails. Okay, this is very easy, right? Represent the bias. Okay, to represent the bias, we'll use theta parameter. And to represent the total number of heads for n number of tosses, we'll use the y variable. So y represents number of heads in n trials. Okay? So according to Bayes' theorem, we have to specify the prior p of theta and likelihood p of y on condition of theta. Okay? So for p of theta, well, we don't know. Okay? It depends on, where we get the coin from, right? But when you are given theta, if you are given the probability that the coin flip is head, okay, then we can compute the probability of y, okay, given theta and the number of trial n. That one we know, right? So let's assume only 2 outcomes are possible. I mean, of course, remember I told you, the coin flip can only be head and tail. I mean, a certain case, the coin can stand up, okay, meaning no head, no tail. But that's a rare case we can ignore. Okay, let's assume that never happens. Okay, so let's also assume coin toss does not affect other tosses. Okay, so when you toss a coin, it doesn't change the nature of the coin. If the coin toss change the nature, for example, if you toss this coin once and the coin somehow, when it hit the ground, it's somewhat like a bend, then obviously the next time you toss a coin, the probability changed, right? So it's just like the cube dissolve example. Okay, the first time you do this experiment is not going to be the same as the second time you do this experiment. I mean, for these 2 samples, some part has changed. So we assume that's not the case. Okay, because we assume coin is much sturdier, much stronger. Okay. So we'll further assume all coins tosses come from the same distribution. Okay, so based on this, assumptions. Okay, there's a random variable coin toss is an example of IID variable. Okay, these assumptions are important. Without those assumptions, we don't have IID variable. Okay, and it will become much more difficult. So this assumption should be reasonable. Okay, if you don't agree, then it's going to be much more complicated, as I say. So given those assumptions, okay, and the likelihood is the binomial distribution. So you have n number of tosses. If the chance to get ahead, okay, for a coin flip is theta, okay, the probability of getting y heads out of these n tosses is this one, right? I hope you still remember this, from your high school math. This is high school math, right? High school math, okay? So, let's still do it, okay, even though it's high school. Okay, so you have n coin flips. Okay, so you have y, okay, head, and you have n minus 1, n minus y tail, right? So the chance to get the y head is theta to the power of y. The chance to get this many tail is y minus theta. Okay, n minus y. Okay, so you get this one. But how many possible, for example, like if you have three trial, and to get like if n is 3, y is 1, then you can be h t t t h t t TTH. So basically, it's like 3 divided by 1, 2, right? It's like 这叫什么？组合数，是不是？ Yeah. So basically, you have like n divided by y and n minus y. Okay, factorial. So this is that one. So this probability is called a binomial distribution, actually. Okay. So binomial distribution is discrete distribution. Okay. Depending on the value of y, you have a different probability. So here, okay, in this formula, there are 2 parameters actually. Okay, n is fixed. N is not a parameter. Okay, theta is a parameter. Y is a parameter. But here, okay, when we say this is a distribution, what we are saying is that, okay, we are using y as an x-axis. Okay, so that's why, okay, 2 things, okay, because y is an integer, so that's why this is a discrete distribution. And also, okay, because we use y, okay, so summation y starting from 0 to n, this formula will add up to 1. Okay, but if you use theta, okay, obviously theta can be ranged from 0 to 1, right? Okay, so obviously, you can also use theta to consider this formula and fix y, obviously. But in that case, this is not a distribution. Okay, this is not a distribution because integral from 0 to 1, given this formula, d theta, is not 1. Okay, it's not 1. Okay. So given a fixed value of theta, okay, this is a probability distribution of y for y. So this here we give you some example. Okay. So where n is 1, okay, and y is 0, y is 1, okay. And theta is 0.25. Represent the upper left corner. And this one is theta. We change the theta value to 0.5. We change the theta value to 0.7. And this one we change the n to be 2. So we have 3 possible cases for y: 0, 1, 2. Okay. And again, we use 0.25. 0.5, 0.75. And when theta is, when n is 4, we have 4 possible cases for y. Okay, so you can see, obviously, I mean, here we give you some examples for this binomial distribution. Okay, for different theta and n. Okay, and you can see that these bars, okay, I mean add up, okay, to be 1, okay, across all the value of y. These bars add up to be 1. Okay? So binomial distribution is a reasonable choice for likelihood. We can see that theta indicate how likely it is to obtain a head toss. Okay? So just compare the value of theta with height of the bar for y equal to 1. So this is from the upper row. Okay, you can see, well, it's a reasonable. Okay, so if we know the value of theta, the binomial distribution will tell us the expected distribution of heads. The only problem is that we do not know theta. Okay, because, well, we do not know theta. I mean, here, I mean, we actually are talking about the prior of theta. Okay, but do not despair in Bayesian statistics. Every time if we do not know the value of a parameter, we put a prior on it. Okay, if you don't know, so this sentence is important. In Bayesian statistics, every time if we do not know a value, okay, of a parameter, we put a prior on it. This is always the case. Okay. So, well, it's 55. Let's take 10 minutes break. When we come back, we'll continue this example. Okay. Okay, it's a normalizing term. So after we get all those things, okay, multiply, and then we get those values. We add them up. Okay, and then divide every one by that denominator. Okay, that add them up. The result, the sum is this one. Because eventually this is going to be a distribution, right? So result is going to be, if you use a computer to run this is going to be just a snap. So quick, okay? Of course, this doesn't need a computer because this is a discrete version. So easy, okay? So easy. It doesn't involve like integration at all. Okay? So we get this. So this one, if you look at this one, this is, as I said, this is posterior, right? So if you look at this posterior and the prior, you see they are slightly different, right? This is a prior, which is centered at 0.5, right? Right? But this is posterior, which is, well, it's still centered at 0.5, but obviously, these values going down a little bit, right? This value going up a little bit, right? So it becomes like this, right? Even though the center is still 0.5, but it looks like it's shifting, right? It's a little bit shifting to the right, right? Right? But this is nature. Why? Because we toss one time and the result is head. So it actually suggests that suggests that the chance of getting head seem to be a little bit higher than just fair, right? Okay, so that's why we get this one. Okay? So can you do this for more number of tosses, obviously you could, right? Depending on, how many tosses and how many head you collected. Okay, so you can do this. Okay, so okay, basically I already explained. But this is just an explanation of what I just told you. Okay, consider theta equal to 0.2, scanning vertically across panel. In the lower panel, 0.2, the posterior probability is likelihood from the middle panel at theta equal to 0.2 times the prior, okay, which at the theta equal to 0.2, divided by the sum of all the results, summation of all the results. That's your evidence, or that's your, that's this term, P of D. Okay, the normalizing term. Okay, so the result, is going to be, like this. Okay, so the overall contour of the posterior distribution is different from the prior distribution, as I already explained to you. Okay, so obviously you can do the similar calculation. Okay, oops, sorry. You can do the similar calculation. Okay, given different number of samples. Okay, so this is we have let's look at these three figures. Okay, the vertically. Okay, we have this prior. Okay, this prior is similar to what we had, which is centered at 0.5. Okay, and linearly, decreasing on both sides. Okay, and you may ask, what is this this range from 0.112 to 0.88 represent? Okay, let's not worry about that for now. Okay, we will talk about that later. Okay, that's called HCI. Okay, 95% HCI, but let's not worry about that. We'll talk about that later. Okay, so so we have that prior, and this is the likelihood that you can obtain. Okay, when n is 4, z is 1. So out of 4 tosses, you get 1 head. Obviously 3 tails, right? So you can, because here obviously, like originally we only consider 11 positions for theta value, right? Originally we only consider 11. Well, to be exact, we only consider 0.0, 0.1, 0.2, blah 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 to 1.0. Only 11 positions for theta value, right? But now, because we are, this one we are actually using computer to draw it, so we are able to consider much denser theta values. So I believe we consider maybe like 1,000 or 10,000 like theta values in between 0 to 1. So that's why the drawing looks like continuous. Okay. And also this one, okay, for each different theta value, you can get, different value from that binomial distribution, right? Okay, providing the theta value, providing the n, providing the y, okay? So you can draw this one. And then from this one, you can multiply these two to obtain this one, right? Okay, obviously you also need to normalize this. Okay, but you can see that, okay, actually, okay, this one, okay, is moving slightly to the left, right? Okay, this is this posterior moving, the center moving slightly toward to the left, right? And this is normal. This, fits into our intuition. Why? Because out of 4 ptosis, we only get 1 head, right? So the chance of the head looks like it's lower than 0.5, right? Even though we have that prior, but based on the current experiment data that we collected, it looks like it's moving to, the chance of getting head is slightly lower. So you can see that we are moving toward the left, okay? And this, on the right-hand side, these 3 figure, okay? The upper figure, okay, is the prior. That prior is actually exactly the same as the left-hand side prior. Even though you look at, oh, how come the center looks like it's a little bit lower? Really, they represent the same prior, okay? It's just because the y-axis, the scale is different, okay? In this one, the y scale is larger, so that makes the height a little bit lower. But they are both exactly the same prior. They are centered at 0.5 and linearly going down on both sides, so they are exactly the same. Okay. And then in terms of data, that's interesting. Okay. Here, okay, obviously we are talking about the same, binomial distribution, obviously, right? Okay, but now, okay, for the data that we collected here, okay, from the experiment, we do 40 trials. We throw the coin 40 times, and we get 10 heads. Okay? So you can see that, okay, we also have 1/4 of the result to be head, right? This one we have 1/4 of the result to be head. This one we have 1/4 of the result to be head. But using the exact same binomial distribution, this is what you get. You will find that they actually both max at approximately the same place, which is 0.25. This is, well, again, this fits our intuition because, well, we get 1/4 of the result to be head. So this one, the highest place is 0.25. This one, the highest place happened at 0.25. Both are like that, which is, well, which makes sense, right? But on the left-hand side, this likelihood is much more, much more slim, right? The 0.25 part is much higher than this one. Well, you may say, oh, they have the same height, but again, be very careful because we are using different scale. This one actually is narrower and wide and high and taller. Okay, than this one. Why is that? Because we have more data, right? We have more data. Okay, if you have more data, you should be more confident in the result of your data. So as a result, okay, the posterior, as you can see, okay, it moved much more closer to 0.25, right? Originally, this one, we only move a little bit towards 0.25, but this one will move much closer to 0.25, right? And it makes sense, right? Because we are using the same prior. The same prior, but the left-hand side, right, for the left-hand side and for the right-hand side, because we have more data on the right-hand side. So we should, we should move more toward what the data suggested. As for how much we should move toward that, it depends on the Bayesian, the Bayes rule. It depends on the Bayesian data analysis. Okay? That's exactly a Bayesian analysis. Okay? So these two, okay, the difference is the amount of the data, okay, but the percentage or like the portion of the coin flipping to be had is the same, okay, and for these two, okay, we are pretty much using the exactly same. We are collecting exactly the same result. Okay, left hand side we collect like 4 toes and 1 head, and the right hand side we have like 40 toes. Out of 40 toes we have 10 heads. Okay, so you can see the likelihood are exactly what just like what we have here, right? They are the same, but the difference is that, okay, we are using different prior. Okay, the left-hand side is more non-committal. Okay, meaning we do not know much about a more plausible theta value. So, well, it is not exactly uniform distribution, but it's very close to uniform distribution, right? So that means we are non-committal. We do not know which value theta is more plausible. We still center at the 0.5, but the difference is really not that much, right? That's the left-hand side, the prior for the left-hand side. On the right-hand side, yeah, we are very, very sure, okay, we get this coin. The left-hand side is more like we get a coin from the magic shop. The right-hand side is more like we get a coin from the government. So we have high confidence that this coin is fair, right? And with different prior. Okay, this one, okay, with these two, you can see the result is almost completely dominant by the data, right? This posterior is almost completely dominant by the prior because the shape looks exactly like the likelihood, right? Okay? Even though the data is weak, we don't have much data, even though the data is weak, we still are able to, the data still control it because the price is even weaker. Price is very weak, right? Okay. On the right-hand side, okay, even when you have 40 toes, the data, we have much more data, but because the prior is strong, so you can see that, yeah, I mean, the result somewhat, is in between these two, right? With a much stronger data, I mean, we still not, you can see like the previous slide, okay? These two are almost identical, right? Because the prior is not that strong. And with more data, the data dominate the result, right? But now we have a much stronger prior, so the result is the compromise of these two. And one thing I also want to remind you is that, okay, for all these figures, you can see we have the prior, we have likelihood, we have the posterior. But prior and the posterior are distribution. They are probability distribution. In other words, their integral is 1. But you can see that we actually indicate that this is HCI, but don't worry about that. You can see we only mark these 2, right? The HCI for these 2, but not the likelihood. Why? Because likelihood, likelihood is not a distribution. Because, you say, hey, wait. Previously we say like a binomial distribution. I say it's a distribution, right? So how come you say binomial distribution is not a distribution? Remember, when I say binomial distribution is a distribution if the x-axis is what? If x-axis represent the number of flips, the number of heads, right? If the x-axis represents number of heads, then it's a distribution. But the binomial distribution, if now the x-axis is not a head, it's theta, right? It's theta. So if you consider the function of binomial distribution, and you use theta to draw the x-axis, then it's not a distribution, okay? Even though it looks somewhat like a distribution, but it's not. In other words, the integral not necessarily will be 1. It's not necessarily 1. Okay? For the likelihood. That's why we call it likelihood. We don't call it likelihood distribution. It's just a likelihood. Okay? Be very careful here. So, well, that's the end of this example. Any questions so far? We still have 10 minutes. I think I'll probably will have just enough time to talk about the definition of the beta distribution. Okay, as you can see that. Okay, you can see that we for the prior here, we still use the discrete prior, right? I just try to have so many points. Divide like the range between 0 and 1 into so many points, so that it looks like a continuous, but really, for this, 4 cases, we really the case we really consider are discrete, okay, are discrete, but when you consider prior, because shouldn't we consider like a continuous case? Okay, but once it comes to the continuous case, then, well, it's going to involve like a integral, as I said. The integral is the difficult, right? It's difficult, but we could consider a certain prior that makes our case easier. That's the conjugate. Okay, the conjugate. Okay, and for the conjugate, okay, prior, okay, it depends on the probability. On the likelihood. For different likelihood, you have different conjugate prior. Okay, for binomial distribution, I should say binomial likelihood. The conjugate is the beta distribution. Okay. So what is beta distribution? Okay, so beta distribution is defined like this. Okay, it's a very common distribution in Bayesian statistics, and it looks as follows. Okay, P of theta equal to this thing called gamma. Okay, gamma function, gamma alpha times gamma beta. Okay, as denominator. And on the top is gamma alpha plus beta times theta alpha minus 1. 1 minus theta beta minus 1. Okay, so it's a little bit complicated, but you will see that this beta distribution has a very good property later. Probably not today, because today, I mean, we only have like less than 10 minutes left. So I can only introduce this beta, this gamma distribution. Sorry, the beta distribution, okay, which is based on the gamma function, okay. So if you look carefully, okay, you can see beta distribution looks similar to binomial, okay, because, well, you can see the binomial, we have a combinatorial number in front of it, and then we have theta to the power of something, and 1 minus theta to the power of something. In terms of shape, it looks similar, right? I'm not saying they are the same, but in terms of shape, they look similar, okay? So, except for the first term, the one with all those gamma, okay? The first term is a normalizing constant. Okay, this one is a normalizing constant. Gamma alpha times gamma beta, this is normalizing constant. Okay, that ensures the distribution integrates to 1. Okay, and gamma represents gamma function. We can see from the preceding formula that the beta distribution has 2 parameters, alpha and beta, obviously. Okay, so here, just want to give you an idea, okay, what beta distribution looks like. Okay, so we have we have 4 columns, 4 rows. Okay, and you know, with different alpha and beta values. Okay, so you can see for the same row, okay, we have the same alpha value, but with different beta value. The beta value increase, okay, from left to right. For the same column, we have same beta value, but with different alpha value. And again, alpha value increase from the top to the bottom. Okay, so you can see that, okay, when alpha and when alpha is higher than beta, okay, or put it another way, alpha increase, okay. For example, like here, okay, alpha, say we take this one, okay, you can see alpha equal to 0.5, beta equal to 2.0. When beta stay the same, but alpha increases, you can see that the height, the center, or the height of the curve moving toward to a right, right? Moving toward to a right. But when beta increase, alpha stays the same. Okay, for example, like here. The max of the curve moving to the left, right? So that's first thing you need to remember. Alpha help the max moving to the right. Beta value help the max moving to the left. But if alpha and beta value both increases, what happens? You can see this diagonal. When alpha and beta both increases, they are more and more concentrated at the center, right? So because it has these 2 parameters, it is very flexible distribution. We can use it to model stuff very easily. Okay, you can see that it even include when alpha and beta are both 1, we can even include this, this is pretty much like a uniform distribution, right? So uniform distribution is a special case of the beta distribution. Okay, so beta distribution is very versatile. That's the first thing, we know, which is good. Okay, so I think I already, so as alpha and the beta, okay, they are put A, B, but you get the idea. Gets bigger together, the beta distribution gets narrower. Okay, the values alpha and beta are called shape parameters of the beta distribution because they determine its shape. Okay, so alpha beta called shape distribution parameters, shape parameter. The shape parameters can have any positive real value. They cannot be negative. Okay, in beta distribution, alpha and the beta, some textbooks say A and B, but you get the idea. Okay, so they can only be positive real number. Okay, and we can use the beta distribution for the prior of theta. Okay, because first beta distribution is restricted to be between 0 and 1, which is in the same way our theta parameter is. Remember, when we throw the coin, the probability that the theta represents the probability that the coin flip is head, right? So that it can only be, the value of theta can only be in between 0 to 1, right? And which is like also the same case as beta distribution. Okay, because you can see here, okay, we only draw, this curve, okay, between 0 and 1. Okay, second, okay, its versatility, okay, as I say, like it has many different shapes. Okay, so distribution adopts several shapes, all restricted to 0 and 1, of course. Okay, so which include uniform distribution and the Gaussian-like distribution and the U-like distribution. U-like is like here, okay, obviously the upper left corner. And the Gaussian distribution is like Gaussian-like distribution. It is not really Gaussian, but it's similar to Gaussian, which is like this, right? This looks like bell shape, right? So, so it's very versatile. You can sort of include like all type of shapes. You can consider all type of shapes if you use the beta distribution. The third one is beta distribution is the conjugate prior of the binomial distribution. What is conjugate prior? It means like we can solve this the integral. Okay, mathematically solve the integral, which was not possible in many other priors. Okay, so this is like the third reason. Actually, the third one is the most important reason. Okay, but for that, I think we don't have time to talk about that today. Okay, so probably we stop here. Okay, next time we start from here, the conjugate prior. Okay. So, any question? And remember, okay, that the questionnaire, okay, I will post that as like a bonus for homework 1, and it will account for 20 points. At the end of the questionnaire collection, I will get the names, who fill out the questionnaire, and and add 20 points to your homework 1, basically. Okay, of course, I will post it in the EE class for you guys. Okay, so please remember to do it. 是用有限的，是不是？Okay. Yeah. Okay. So let's get started. The homework one. The due date was yesterday. Is that right? Okay. Yeah. Shouldn't be too difficult, right? Okay. So. So let's continue. Okay. I plan to give like the second homework like in another 2 weeks. Okay. After finish this chapter and maybe like a little bit into the next one. Okay. So last time we talked about the beta distribution, right? I mean, it looks like, the formula looks like this. And where this is gamma function. So in this formula, okay, let me remind you once again, okay, the parameter, I mean, for the gamma distribution is theta, okay? It's a distribution over the parameter theta. In the range of 0 and 1, okay? And alpha and beta are what we call shape parameters. They control the shape of the beta distribution. I mean, depending on the value of alpha and beta. I mean, some paper or some books said these are A and B, but they represent basically the same thing, okay? So the different value of alpha and beta, I mean, cover a lot of shapes. Okay, it has like skewed to one side, such as like where alpha is lower than 1. Beta is like increasing, okay? So you see it is skewed to like a left-hand side. Or it can skew to the right-hand side where beta is lower than 1. And alpha, I mean, is, over 1. So that's the case when the figure is like skewed to the right. Or it can be, with one max value, okay, that's where when alpha and beta are both greater than 1, okay. When alpha and beta are both 1, I mean, the beta distribution also cover uniform distribution, so which is nice. So it has lots of different shapes, okay. And I think I talked about like these conclusions. Okay, did I finish this slide last time? I kind of forgot like which slide I end up with last time. This one or the previous one? Okay, so we haven't we haven't covered this one. Okay, so actually this slide is pretty much, I mean, already covered, I mean, in my description of the beta distribution, because you can see beta distribution is restricted between 0 and 1, okay? I'm talking about the theta parameter, okay? So so in general, we use beta distribution when we want to model proportions of a binomial variable, because it is in between 0 and 1, which make it, I mean, very suitable to be used for that purpose. Okay, I mean, to model a proportion. Okay, and its versatility. I mean, we like the beta distribution to be used for prior is because it covers so many different shapes, okay? And the beta distribution is the conjugate prior of the binomial distribution, but I don't think we cover conjugate prior last time, okay? So what exactly is the conjugate prior? Okay, conjugate prior is has a very good property. Of course, okay, when we say a distribution is a conjugate prior, I mean it is to a certain likelihood function. Okay, for example, beta distribution is a conjugate prior of binomial distribution. In this case, the binomial distribution, I probably shouldn't say binomial distribution. I should say binomial likelihood. Okay, binomial likelihood. Okay, so a conjugate, okay, prior must be correspond to a certain likelihood. Okay, and the conjugate prior, okay, of a likelihood, okay. What do we mean by a conjugate prior is that, okay, remember, if you have a prior, you have likelihood, you are able to get a posterior, right? Okay, we used like remember like a coin flipping, okay, example previously. But remember at that time, we use numerical approach, right? When I say numerical approach, I mean like, we just sample like 1,000 point between 0 and 1, and then, draw that curve by using like those sample points. It's I'm referring to this thing. Okay. Yeah, remember, I mean, this is like a sample of 11, we have 11 samples here, but for the figures here, we put like, I believe we use 1,000 samples so that it looks like they are continuous, but actually they are not. Okay, we are using like discrete cases to get these shapes. Okay, I'm not saying, okay, the numerical approach is bad, but numerical approach sometimes it has its shortcomings. Okay, think about that. I mean, when you have a lot of parameters, I mean, it is going to, if you try to do a sampling, okay, for each distribution, you are going to end up with a lot of points that you need to calculate. Okay, it could be, so big that even the modern computer will have a hard time to do the calculations. Because right now, the example that I showed are one-dimensional. Okay, it has only one parameter, theta. But in the real world problem, we have like tons of parameters. I mean, even literally like tens of hundreds of parameters. So in case like that, okay, if you try to get like 10 sample points for one dimension, consider if it's like 100 samples, then it's going to be 10 to the power of 100, because the sample point, for different dimension, when you want to accommodate different dimension, it's multiplied, right? The number of samples is multiplied, okay? So it's going to be so big that the modern computer cannot handle, okay? But having said that, okay, this simple approach help us to get a feel of like the Bayesian inference, in the sense that when you have a prior, you have a likelihood you can get a posterior, right? Okay, like numerically, of course, at that time. But if the prior is conjugate prior, the good news is that you can analyze it. You can analyze it so that, here, okay, if the prior is a conjugate, okay, and then coupled with the corresponding likelihood, okay, the posterior will, be the function just like this prior distribution. Okay, of course, you'll have different parameters. Okay, let me repeat. Okay, it's interesting. Okay, if the prior is beta distribution and the likelihood is binomial, then the posterior can be proved that it's going to come back to beta distribution. Okay, analytically. Okay, what does that mean? That means that you don't need to worry about, sample points. Okay, it is, it can be derived. Okay, so obviously it's a very good property, right? Okay, it's a very good property. So, the beta distribution being a conjugate prior for the binomial likelihood is not the only conjugate prior. Okay, there are other conjugate prior. For example, okay, the normal distribution is a conjugate prior of normal likelihood. What does that mean? If the prior is normal and the likelihood is normal, then the posterior will also be a normal distribution. Okay, that's what it means. Okay, and I will show you, okay, why the beta distribution is a conjugate prior later, okay, today. Okay, so for many years, okay, Bayesian analysis, okay, was restricted to the use of conjugate priors. Okay, obviously, this is a big restriction. Okay, because for conjugate prior to exist, okay, it has a lot of requirements. For example, your likelihood function need to be a specific ones, okay, a special one, so that you have a conjugate prior, okay. But it is not necessarily the case, okay. Remember, like the binomial likelihood, okay, was there. It's just because remember we used the coin flipping example, right? So when you analyze it, the likelihood happened to be binomial. Okay, it's not like we just assume the likelihood is binomial. You cannot do that. Okay, prior can be assumed. Prior distribution can be assumed. Okay, so if for prior distribution, beta distribution is good because, as I said, it's a versatile. It covers so many shapes, so it's good, very ideal distribution. Because whatever a lot of cases when you think about a certain prior, the beta distribution you can sort of set up the alpha and the beta value so that the beta distribution look like that shape. Okay, but that's for the prior. Okay, for likelihood you cannot set it up. Okay, you sort of have to derive it. Okay, depending on the problem. Okay, so this is if you want to solve the posterior, okay, using the Bayesian analysis, okay, in the past, okay, if you want to solve it analytically, okay, you are restricted to use the conjugate prior, okay, because otherwise a lot of time, okay, because when you derive the distribution of the posterior. I mean, it involves like the integration that is so complicated. Like you know, you can only deal with it by numerical approach. But the numerical approach has its shortcomings, as I already mentioned. Okay, but this was a deal breaker. Okay, before the development of suitable computational methods to solve probabilistic methods. I mean, nowadays, okay, I mean, here we still, discuss like how to solve this, how to use conjugate prior to solve this analytically. But later on, okay, this restriction is no longer there. Okay, is it because our modern computer is so powerful that we don't care about like a sample space? No. Okay, it's because of spatial sampling methods. I mean, not one spatial sampling method. There's a slew of like different sampling methods being developed like in the recent 30, 40 years. Okay, by mathematicians. Okay, and those sampling methods are very powerful in the sense that even if you have a very, very large sampling space, I mean, with a very high dimension, okay, you don't have to really sample every grid point, and you can still get the job done. Okay, you can still draw the posterior distribution. But that's the, I mean, we are going to talk about those concepts like not in this chapter, but in the future. Okay. So we can think of alpha and beta, or A and B, whatever you call it. Okay, for beta distribution in the prior, as if they were previous observed data. What do we mean? Okay, in which there were alpha heads and the beta tails in the total of A or alpha plus beta flips. Okay, so you can assume, okay, because originally, if you don't know anything about this problem better, okay, sometimes you want to use, because you are going to use alpha and beta or A and B to describe your belief, right? Okay, so remember, like we say, like, okay, I mean, you get this coin, okay, from bank, okay, so you have maybe like a moderate, like confidence that it is fair. But how do you describe, that using the beta distribution? You can do it something like this. Okay, if you have no prior knowledge over, then the knowledge that the coin has a head side and the tail side. Okay, you know nothing about this coin. Okay, you don't even know where this coin comes from, but you know it has two sides. Okay, then you can say, okay, you can set like alpha and the beta both to be 1. Okay, in that case, okay, your prior will be uniform distribution. Okay, here, this one. Okay. This one, the flat one. Okay, so this is when alpha and beta are both 1. Okay, well, because you know, like, we have a tail, we have a head, and you can assume that you have flipped this coin twice, and you get 1 head and 1 tail. That's pretty much about it. Okay. So, okay, if you think that the coin is probably fair, it's probably fair. Okay, as I said, we get it somewhere. Okay, maybe from the bank, but it's not directly from the government. We are not very sure. Okay, then we can imagine that the previous observed data had, say, alpha and beta both to be 4. Okay, here we are describing, not so confident face that this coin is fair. Okay, we believe coin is fair, but we are not so sure. Okay, because remember, when both alpha and beta are the same value and they are larger than 1, then it means that we have a bulk at the middle, right? If you look at the diagonal figure, okay, especially like the lower right one, it's alpha equal to 3 and beta equal to 3. I mean, as alpha and beta are both to be 4, you can imagine this bulk will become even more obvious, right? Okay, it's going to be more concentrated. The distribution is going to be more concentrated on 0.5, but just a little bit more concentrated, not so concentrated, okay? Because you can see the trend, yeah, it's going to be a little bit more concentrated, but just adding one to alpha and beta, okay, I mean, to the lower, I mean, right corner, okay, case, I mean, it's not going to affect that too much, okay? So, but still, it describes a mild belief that the coin is fair, right? So, so often we think of our prior belief in terms of central tendency and the certainty about the central tendency. Okay, so central tendency and the certainty about the central tendency, they are two things. Okay, central tendency describes like where the center should be located. Okay, and certainty about the central tendency is how concentrated your distribution should be, okay, to a particular center. Okay, so if we use like traditional statistics as an example, the first term normally can be considered as mu, okay, the average, okay, and the certainty about the central tendency. A lot of time we consider that in the traditional statistics as sigma, the standard deviation. Okay, as you know, like when standard deviation is large, like the figure will be more concentrated to the mean, right? We know that, right? Okay, so so actually, okay, in thinking about probability of left-handedness, okay, in the general population of people. So, by the way, how many people in this class are left-handed? Do you mind like raise your hand? Only one. Yeah, two. Okay, so I mean this is like a cultural issue. Okay, I mean like in Eastern culture. Okay, the parents sometimes don't like their kids to be left-handed. So even if you are left-handed, okay, when you are little, okay, the parents may, correct it, okay, in the sense that the parents will force you to use the right hand, and but really like in other countries, especially Western country, I mean, the left-handedness, okay, is not an issue. Okay, they consider this as just like like hair color. Okay, like or like eye color. Okay, just attribute. Okay, of a human, and it is very convenient, okay, as far as I remember, like when I was in US, okay, even though I'm not left-handed, okay, I know like there are a lot of places that sell like items, especially designed for left-handed people. So it's very convenient, to be left-handed in Western country. Unfortunately, in Taiwan or in most of like Eastern countries, like you see like left-handed people like ratio is very low. okay, it's not really, it's really because like the cultural issue, okay? See, okay, I mean, from everyday experience, that is around 10%. I mean, the left-handed population. This is the case in Western country, not in Eastern country, okay? So if I'm not very confident about that value, we might consider equivalence. I mean, previous sample size to be small. For example, n equal to 10, which means that of 10 previous observed people, one of them was left-handed. Okay? So how do we set up alpha and the beta value for a beta distribution to describe that? Okay? In this case, the alpha, you can set alpha to be 1, beta to be 9. Okay, it's kind of just like you have 10 trial, and out of those 10 trial, 1 is left-handed. Okay, so 1 is like so A or alpha is 1, B or beta is 9. Okay, or in thinking about the probability that the government minted coin come up heads, okay, such a probability should be very, very near 50%, okay? So because we are fairly certain, okay, we can set this equivalent previous sample size, okay, to be maybe n equal to 100. So here, okay, what do we use to describe this the certainty about the central tendency? It's the value of n, which is the sum of alpha and beta. Okay, if you are not so certain, you can set n to be smaller. If you are pretty sure, for example, like you consider the government minted coin, okay, it's pretty fair, okay, you can set n to be 200. In this case, of course, because it's fair, so you have half of the them to be A and half of them to be B. Or let me put it this way, you can sort of consider A or alpha to be the number of flips that come up head, and the B or beta to be number of flips that come up tail. Okay, so you can use that, okay, to determine the A and the B or alpha and beta value, I mean, for your prior distribution. Okay, so our goal is to convert the prior belief expressed in terms of central tendency and the sample sizes. Okay, so using the A and B value, okay, in the beta distribution. So in that case, I mean, as I said, I mean, we normally consider the central tendency as a mu, the average, and the standard deviation to describe the certainty of that central tendency. Okay, so for beta distribution, okay, the mu is actually A divided by A plus B. Okay, so so you can see that, okay, it is very reasonable, okay, to consider A is 1, the B is 9 in the first case, okay, that to describe like the portion of left-handed people, right? Because the mu is going to be 1 over 10, okay, which is the 10%, right? And the omega. So what is omega? Omega is the mode, okay, mode, okay, 众数. Omega is mode, okay. You could describe central tendency using 2 different ways. The first way is to use the mu, the average, or expected value, okay. The second one is the mode, okay. Either one works, okay. Either one works fine, okay. And for mode, it's a little bit more complicated. It's A minus 1 divided by A plus B minus 2, okay. For if the A and the B are greater than 1, okay, which is normally always the case, Okay, so and by the way, when A and B are the same, okay, we know beta distribution will be symmetrical, right? When beta distribution is symmetrical, obviously you can imagine the average will be the same as the omega, okay, 众数跟平均会一样 okay. So when A equal to B, the mean and the mode are 0.5. I mean, you can actually calculate that easily, okay. So when A greater than B, I mean, obviously the mean and the mode are greater than 0.5. When A smaller than B, the mean and the mode are less than 0.5. You can verify that easily by using the above equation, okay, or by observing the figures here. Okay, very easily, okay. So, okay, and the spread of the beta distribution, okay, how certain you believe the central tendency is related to concentration. Okay, the concentration, we say this concentration is A plus B. We give it a particular name, okay, to this value. We say this is kappa. Okay, the kappa describes how concentrated, okay, your beta distribution is. Okay, so as kappa gets larger, the beta distribution will be, more concentrated toward the center. Okay, and obviously you can, when you have the mu and kappa, okay, if you have a mu and the kappa, you can get your A and the B value. Okay, so A will be mu times kappa, B will be 1 minus mu times kappa. Okay, so this is the case when you have mu and kappa. But to be honest, kappa is really not something that you that can be described like intuitively. A lot of time, maybe what you have, okay, is something different. We'll talk about that later. Okay, but if you have the omega, okay, omega actually is more intuitive than mu. Why? What is mu? Mu is average, right? So when the distribution is not symmetrical, okay, the average normally will not be the highest place in the distribution, right? Okay, for example, if I have a distribution like this, you can imagine the average, okay, will be, this is the highest point, okay, but the average of this distribution should be somewhere here, right? This may be your mu, this will be your omega, right? So omega is more intuitive. In a sense, it represents the highest point, the place that will give you the highest point in your distribution, right? So omega, okay, if you have the omega and the kappa, okay, we also have the formula that tells you how you can set up your A and the B, okay? I mean, omega times kappa minus 2 plus 1 is your A, and you can set B to be 1 minus omega times kappa minus 2 plus 1, okay? So this work well for kappa greater than 2. You may say, oh, so kappa has to be greater than 2 for that for this formula to work. But kappa is usually almost always greater than 2 anyway. Okay, because kappa represents the concentration, which is A plus B, remember? And we normally use the value of A, B greater than 1 anyway. Okay, for your beta distribution. So, as I said, the concentration, the kappa, is not so intuitive. The reason is just like the relationship between mu and omega. Omega is actually more intuitive because it represents something more obvious to be observed. I mean, kappa, well, how do you describe like your belief in kappa? That's probably hard to say. So, okay, you could, use, mu and the sigma, the standard deviation, okay, to describe a beta distribution. Okay, however, okay, using this way to describe a beta distribution, I mean, you should be very cautious because the sigma here, okay, cannot be assigned arbitrarily. Okay, there's it has to make sense. It has to be to make sense. I mean, when you give the sigma value. Okay, so in particular, the sigma should typically be less than 0.28867. This describes like a plausible, a more convincing value. Okay, the range of the value for the beta distribution. So that's the standard deviation of a uniform distribution. So our beta distribution is sigma. The standard deviation is less than the standard deviation of a uniform distribution. Okay, and when you have your mu and the sigma, then you can also use the lower equation to get your A and the B value, okay, for your beta distribution. So here, okay, we are trying to tell you ways to convert your belief, okay, the central tendency and the certainty to that central tendency. Okay, either you use mu and the kappa, or mu and omega and the kappa, or mu and sigma. Okay, to obtain your A and B here. Okay. So now, okay, it's a time to talk about how we can derive the posterior, analytically, okay, using the beta distribution. Okay, let's look at these formulas. Okay, these formulas are actually very easy, even though this is you see a lot of formulas here, but don't worry. Okay, the only thing you need to worry is the last step. The last step may need more explanation, but other than the last step, most of them are pretty much like straightforward. Okay, you see, okay, given remember the in coin flips, okay, originally theta represent the parameter of the model, right? Okay, so and z and n represent the collected data, right? How many trials you have for that coin flip, and among those trials, how many heads you have, right? Z represent the number of heads, okay, and n represent number of trials, okay. So here, something that we know is a prior. Prior is this one, right? Right? Remember, this is the prior, okay, which we actually described using the beta distribution here, okay? Because we want to use this conjugate prior, and the likelihood, okay, is like given theta value, the data, right? Okay, this is like given the theta value, your data d, right? So, so what you have actually is going to be, okay, because eventually we want to, so we have this. These two things are given. Okay, given. Okay, what we want to derive is, okay, given the data, given the collected data, what is a plausible distribution for the theta? Okay, this is what we want to get, right? Remember, like in the previous lecture, okay? I mean, how we do the Bayesian inference, right? So this is what we want to obtain. So this one is going to be P theta d divided by P d, right? And the upper one is going to be P d theta times P theta divided by, the PD, right? Right? So far so good, right? And the D actually can be written as like Z and N here. Okay, but let's concentrate that this actually represent data anyway. Okay, so let me remind you once again, this represent the prior, this represent the likelihood, and this is given because data is given, so probability of that data, okay, over all possible model parameter, the lower one, PD, is a constant, right? The only thing that, because remember that, okay, this is posterior, right? This is posterior. And in the posterior, think about this. D is fixed, right? D is the data that you already collect, right? D is the data that you already collect. How many trials, how many head? You already have that at hand, right? So this is fixed. The thing that is not fixed is the theta. The theta is something that is not fixed. The only thing you know about theta is the prior. It's a distribution. It's a distribution for that model parameter. Okay, so theta is a variable. Theta is a variable. And so that you know that, okay, this is a distribution over theta. This is also a distribution over theta, right? So because this is a distribution over theta, okay, I mean, you have theta for the terms in the nominators. Theta is here, okay, right? But for the denominator, there's no theta there, right? Denominator is P of D, right? I mean, the theta is nowhere to be found, right? So that pretty much means that this is constant. This is a constant. Or you can say this is a normalizing term. Okay, normalizing term. Okay, sometimes like in Bayesian statistics, we say that's evidence. Remember, we talked about this, the name of this term before. Okay? So far so good, right? You see, up to now, I have not put in any real formula yet. I didn't put in beta distribution. I didn't put in the binomial likelihood, right? I only put like, all the things I put are the, well, you can say that this is like, well, actually, Bayes theorem only, right? Bayes theorem. Okay? So after, what happens after we put in beta distribution, after we put in the binomial likelihood? Okay, let's take a 10 minutes break. When we come back, we will continue. Okay? It's like, you know, the posterior. I mean, okay, and then we use the Bayesian Bayes theorem, okay, to write it down, right? And then, okay, we know our prior is beta distribution, right? And we know our likelihood is binomial likelihood. So here, okay, you see, in this slide, okay, we put in this beta distribution here, and we put in the binomial likelihood here. Okay. As for the denominator, we know nothing about it. The only thing we know is it is constant, right? As I already described. Okay. So we put in these two things, okay, and we can obviously, you know, see that, okay, there are theta and 1 minus theta terms, okay, for both, from both like prior and the likelihood. So we can, you know, rearrange them. We can rearrange them to become something like this, right? Z plus a minus 1, okay, theta to a z plus a minus 1 times 1 minus theta to the power of n minus z plus b minus 1. So from here to here, it's very basic mathematic, like a massage for the equation. Okay, really nothing very special, right? Okay, so far so good, right? So this is what you have. And this is the denominator will be capital B, A, B, which is like the denominator of the beta distribution, okay, with A, B as its parameters. And Z, P of D, okay, P of D, this is the evidence or normalizing term that we don't know what that is. Okay, but one thing we do know, BAB is also a constant, right? Okay, BAB, where is this BAB come from? The BAB actually come from here, right? This one. This is our BAB. The gamma A times gamma B, or gamma alpha times gamma beta. This is, normally we describe it as like a BAB. Okay? So this is obviously a constant, right? This is obviously a constant. Okay? Well, yeah. Not exactly. I mean, it's actually should be. Let me take it back. The BAB should be it should be the BAB is gamma A, gamma B, gamma A plus B. Okay, this is BAB. Well, we don't know what that value is. Okay, we know. Of course, we know gamma is a gamma function. Okay, that we described earlier. Okay, so these terms obviously, you know, are only dependent to A and B, right? And A and B are constant. Remember, A and B are constant. Okay, it's the fixed value that we use for our prior to describe our prior. So A, B are fixed. The data is fixed. A, B term in the prior are fixed too. Okay, so this thing, okay, even though, I mean, of course we could calculate the value here. Okay, we could do that, but we don't have to. Okay, after all, I mean, the only thing we need to know is that this is a constant. Okay. So, okay, back to here. So this capital BAB is a constant, and this P of D, okay, is constant too, right? The numerator, okay, contains the terms that are correspond to theta. So these are not constant. They are not constant. Okay. So from here, okay, suddenly it become this. So remember what I say, like this slide, this slide, okay, is actually, you know, except the last step. All the other part in this slide are very easy, okay, straightforward. Okay, this beginning part, well, you just use Bayes theorem. And then you plug in your beta distribution, you plug in your binomial likelihood, and you massage your formula to become like this. And then why you have this? Okay. You wonder how come this term become this one directly, okay? Here I'm telling you, it has to. It has to. Why? The only step that is magical is the last step. And that last step has something to do with the fact that the posterior is the distribution. Okay, so here okay. Let's consider this. Okay, well, your P. Posterior it should be theta D. Anybody has question with this formula? We know posterior is a distribution, right? Over theta, right? Posterior is a distribution over theta. Then, okay, because this is posterior, right? It's quite lengthy, and you know, this formula looks quite lengthy and complicated. But we know it represent posterior distribution, right? Nobody have question about that, right? So, okay, let me plug in that formula to here. okay, it should be, okay, I can even write the lower and the upper, limit, okay, for the integral, okay. It doesn't matter actually, okay. And then we just theta to the power of z plus a minus 1, okay. Z plus a minus 1, okay, times 1 minus theta to the power of n minus z plus b, n minus z plus b minus 1, right? Okay, and then divided by the capital B AB times P of D. Let me just abbreviate it as D. Okay, and then don't forget we need a d theta, right? I mean, actually, it doesn't matter. I mean, you put like a 0 and a 1. I mean, it doesn't matter. Let's not be distracted to those like a detail. So far, so good, right? Right? And so we know this is 1, right? Right? I say the integral of the posterior is 1. So this is posterior. The integral over the theta is 1. I'm doing exactly that, right? And I remember I keep reminding you, the denominator is constant, right? The denominator is a constant, right? So it doesn't matter. We can put, if when you do integral, okay, if the function has a constant, you can get the constant out of the, the integral. Everybody know that, right? Even though you may already forget how to do integral. You at least I expect you guys still remember that, right? You can put this thing, okay, outside of the integration. And then the thing you left will be z plus a minus 1, okay, times 1 minus z, okay, and n minus z plus b, I'm sorry. Minus 1, okay, and d theta. Right, this one is this one, right? Right? And because this is 1, right? So we know this integral will be exactly this value, right? In order for the result to be 1, this integral will be this value, right? Right? Otherwise, how can it be 1? Right? So, okay, so I can, I can directly write it to be something like this thing is this integration, right? So far, so good, right? Okay. Now, let's consider the beta distribution where we use z plus a for the parameter a and n minus z plus b for the parameter b. Okay, let me this one. Okay, let me rewrite it like okay. Let me get rid of this. It's probably easier to that we use beta distribution. Okay, beta distribution. Let me just use beta. Okay, with like a b. Is what? Is theta a minus 1 times 1 minus theta, okay, b minus 1. And then remember I say the rest of the term is BAB, right? 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 So far so good, right? And I told you this is a beta distribution, right? So now, let's think about this. When we put, what is this thing? We put this one as our new A, Z plus A as our new A, Z plus A as our new A, and then N minus Z plus B as our new B. Obviously, these two new parameters are still valid parameters, right? Are still valid parameters. I mean, we actually increase the value of A and the B, right? N minus Z, by the way, N minus Z represent the number of tails, right? Z represent number of heads, right? N is no total number of trials. N minus Z represent number of tails. So number of heads is Z. N minus Z is number of tails. So you are adding value to A and B, so, well, it's never an issue, right? Never an issue. So when you copy this, it's going to give you what? The denominator is going to be beta, B, capital B, Z plus A, N minus Z plus B. Just copy the A and B parameters here. But the denominator is going to be theta to the Z plus A minus 1 times, okay, 1 minus theta. Okay, N minus Z plus B minus 1, right? Is it okay? Is it okay? Any question with that? I'm just, writing down the beta distribution, right? Right? I'm not changing much from the beta distribution, right? And then, okay, we know beta distribution is a distribution, right? It is a distribution, right? To be honest, beta distribution should have been written like this. It should have been written. I'm sorry. I mean, I'm sloppy. I'm being sloppy on the notation. Okay, it's a formula. It's a function over theta. Okay, so here, okay, I should have written like theta. Okay, given a and the b value like this. Right? It is a distribution over theta, right? So, having said that, when I do integral over the beta distribution, no matter what parameters I'm giving to A and B, okay, the result should be 1, 2, right? Right? I'm just doing exactly the integral. I mean, you know, so the important thing is here, integral beta theta. Okay, here is like z plus a n minus z plus b. This one d theta should be 1. Right? It is a distribution, right? It is a distribution. Right? So when you plug in this thing to here, once again, this is a fixed term. This is a constant, right? Just like here, once a, b value are fixed, the denominator is fixed anyway. When your a and b parameters are fixed, right? So, okay, it's going to end up telling you that the integration of this part, okay, is going to be the same as your denominator, but this integration is this one, right? So from that integration, it also tells you this thing is right? Okay, in order to show you, the last step makes sense, you need to use the fact, okay, facts, okay. First, this posterior is a distribution over theta. And also, well, beta distribution is a beta distribution, it's a distribution over theta. Right? Once we have these two, well, it's obviously the dots are connected, and these two terms are the same. In other words, this is a beta distribution with the A and B. This one to be A, this one to be B. Okay? Any question here? N 减 z 加 okay, I'm sorry. It should be yeah. Okay? Any question here? This derivation should be pretty straightforward, okay? It involves really nothing but like a very simple concept, okay? So once you acknowledge that, okay, it become very interesting. I mean, first you know that, okay, if the prior is is a beta distribution, and the likelihood is the binomial, okay, you can analytically derive the posterior, which is also beta distribution. So this makes beta distribution conjugate prior for binomial likelihood. Okay? So here I'm just trying to explain what we have already explained. So nothing much to talk about. Okay? But the interesting fact is what? Think about this. Okay, remember I told you, okay, we can sort of consider prior here. We can sort of consider the prior to be how many number of heads and how many number of tails. Okay, I mean, we can sort of consider our prior, like that, and to set up the beta distribution for our prior. Remember? Okay? And then, okay, now the data you obtained has a number of heads and n minus a number of tails, right? Right? The data you collected has a number of heads and n minus a number of tails. And then the posterior you obtained, indicate that it's just like you have z plus a total number of heads, and b plus n minus z number of tails. It's very consistent, right? Very consistent. I mean, if you say the prior, say, oh, I only know, okay, they are two-sided, okay? The coin has two sides. I mean, so I said A and B to be 1. So that, sort of, indicating like you throw the coin twice and you get a head once and you get tail once, right? So A and B both to be 1. Okay? And then say you throw the coin, now you throw the coin 10 times and you get one head and 9 tail. The result is what? The result is a beta distribution using A to be 2, which is 1 plus 1, B to be 1 plus 9. That's exactly what the prior plus what the data tells you, right? Right? So this is very interesting. Okay, this is very interesting. Not only you can observe that, obviously the beta distribution is conjugate prior, but also, okay, it tells you that, okay, the A and the B in your beta distribution, in your beta prior, actually, and also obviously the posterior, okay, beta distribution, okay, the A and B in your posterior distribution, okay, has meaning. They have meaning, right? They have meaning. And those meanings, right? Those meanings make sense. So, here I'm giving you a because now we obtain this posterior analytical, right? So we can actually, we don't need to use the numerical method to get the result. We just say that. So assume
before you have zero trial, zero head, meaning you haven't started your experiment yet. You haven't started your experiment yet. Okay? So, you see, obviously you can see three distributions here, right? Those three distributions represent three different priors. Okay? You can see the blue prior is the flat prior, indicating that we don't know anything about the step, right? So that's why we say it's a minimal distribution, right? And the orange one is like the prior that we are sort of sure that the coin is true, right? Sort of, not very sure, but it is kind of sure, because the mode and the new looks like it is at exactly 0.5, right? And the green one, okay, is it is like skewed toward the situation that the coin is like 10 to flip to 10 to get the tip, right? Because like the highest point for green distribution is 10, the value is omega is 0, meaning the chance of getting 10, okay, is low, right? Low. So, okay, with these three different priors, okay, if you do one throw, okay, you get one prior, and three, you get only one head. Okay, with the above three different priors, this is the result of the theory. You can see that, okay, for the blue one, okay, it's not due to the head. To increase that the head is becoming deeper. Okay, but it's becoming slightly deeper, not so deep. Okay, and the green one, okay, is not so still anymore. Okay, it's moving toward the right. Okay, and then the orange one, because it's slightly more complicated, and possibly much more complicated than the other two. So it is affected by the data a little bit, but not that much. Not that much. You can see it almost maintains almost the same shape. Actually, it is affected a little bit in the green orange distribution. It's affected by a little bit. It's hard to observe because it affects only a little. And then as more and more rows, more and more trials are collected, the more data are collected. You can see the 2 trials and you get 1 head, 3 trials, 1 head, and so on, and so on. Here, I'm telling you that eventually, okay, as you collect more and more data, you can see uniformity of the trials, okay, the posterior, when you have a lot of data, the posterior will converge. Right? You can see when you have 150 trials and 48 out of them is test, then you can see these three distributions sort of like merge together, right? Okay, let's measure why. Because prior is only the pre-knowledge before the experience. But as you collect more and more evidence from the experience, okay, your data should dominate the result, right? That's automation. Okay, very just have the mode to start with, right? And you can see that, okay, they compensate to the, very quickly, they are much closer to each other. But the orange one, because it has a stronger prior, okay, even at the very end of the data collection, you can see that, the orange one is still a little bit far away from the other, right? It's because originally it has a stronger prior, okay? And this also tells you a very reasonable story, because if the prior is stronger, then the data should, remember I told you that in Bayesian analysis, the posterior is a compromise between the prior and the data. Okay. When I say prior is prior, when I say data, I mean the likelihood, right? Okay, likelihood or data, whatever it is. But you can see that, okay, because if your prior is short, okay, yeah, eventually when you collect more and more data, the data will dominate. But because prior is stronger, so this conversion happens lower, right? The conversion happens lower. Of course, when you have maybe 1,000 trials, eventually all this reality of the data prior will approximately totally converge. Okay? So this is the second thing. The third thing that I would like to talk about is that, okay, you could do this Bayesian inference, okay, Bayesian analysis from here, okay, with 0 trial, 0 head, okay, and then you get 150 trial and 48 head. So you from here to here directly, or you can do it like a, from here to this one, and then from this one to here, from this one to here, from this one to here, and so on. You can do one step at a time. It doesn't matter. The result will all be the same. Okay. You can collect data a little bit by a little bit. And then, each time you do analysis. Of course, for example, from here to here, okay, this is the prior, this is the posterior. From here to here, this is the prior. Okay, and the additional three, with a result obviously 10. Okay, that one is the data, right? And so on. So this is from here to here. This is the prior. This is posterior. And the extra data is collected is one tenth. Sorry, 1/10. Okay, and so on. So this tells you that Bayesian data analysis is good in the sense that you can do experiments incrementally. Okay, and the data that is collected, okay, you can put it together and do the analysis all in one, or you can do your data analysis, a little bit by little. It does not affect the result. Okay, it does not affect the result. This, of course, is based on one assumption that this file, this center, this IIT, okay, we talk about it earlier. The fourth one, I would like to compare in this experiment is that Bayesian data analysis, okay, the result, okay, of the data Bayesian analysis, okay, or Bayesian inference is always distributed or like MHFT, okay, those will give you particular value, or you can sort of like use that to verify that a particular statement you can refute a particular statement, something like that. But you know, that's not the case for Bayesian research. In Bayesian research, the result is always represented by a possibility distribution. The possibility distribution contains all the information you need, okay, from this analysis. Okay? The last thing that we may wonder is that, what is that particular black marker, okay, in the future? You see that particular marker in the future. I think that is 0.35. That remember, because this is actually, the data is actually generated by computers. Okay, we use computers to simulate the coin flip. Okay, so that 0.35, that black marker actually indicates the probability the coin flip will pass. We put it in a computer simulation. You have to set that value, right? Okay, so that is the set value. So that's why when as more and more data is collected, because we fall close to 1/3 of them to be passed, right? Close to 1/3 of them to be passed, and 2/3 of them or the required to be passed, because that black marker, okay, is the data value which indicates 0.35, which is about the what over 3. Okay? Of course, when you do the analysis, we don't know that data value. We don't know that data value. But as you collect more and more data, you can see that, okay, the distribution will get closer and closer. The mode of the distribution will get closer and closer to that marker. Right? Even though we don't know that the true data value, okay, it's going to show, it's going to convert to that mode of the distribution. Any questions so far? Okay. Yeah, so then I already finished this slide. It's clear the fire and influence. Okay. So fire is an important part of the Bayesian research. Okay. This is time. Okay, and fires are supposed to do this. Okay. So if you are new to this Bayesian analysis, okay, or like you don't like some traditional statistics, do not like Bayesian analysis, they prefer like a traditional frequency approach. Okay. So they normally will be nervous at how to choose fire. And the fire is a little bit subjective. But it is okay to be subjective on the fire, because it is just like any assumption that you have for your analysis. Okay, you have see, you identify as well as you can read it. Okay, so then after this, they can't really see. Okay, at that, they are meaning. You have to explain the meaning of the data. Okay, and the data same thing in history. The same data will lead people to think differently, okay, about the same topic. This can happen if you base your opinion on formal knowledge. Even if you base on your opinion on formal knowledge, this could also happen. I mean, so a lot of the time, this is because the higher institution, okay, or the model. So some people like the idea of non-important type. What is non-important type? Meaning the fire is flat. Okay, for example, like flat, big, diffuse fire. So such as blue fire that we use. Then, or like this fire is flat. It's not exactly so flat, but we say like this. It's quite flat, right? That's problematic fire. Non-informative fire. So, so this fire has the least possible amount of impact on the land. If the fire is not strong, pretty much the data, the collected data will have the more impact to your opinion. Okay. So for the topic you use a flat fire. Okay. In general, we can do better. Okay. Because the fire represents our knowledge tool is a problem. Okay, if you don't use this knowledge, okay, it's really okay. So during class we will follow the recommendation of German, Elvis, Truth, okay, and many others, and we will refer weekly informative files. Okay. And so you may wonder what these people are. Okay. Gilbert is the primary author of the red book that I use as a reference. And remember I told you there was a good reference. It's for this subject, but I didn't want to use your red book as a subject because that's too difficult. So two mathematics. Okay. The primary author of that is Gilbert. Elliot is also another book. Okay, they are both pioneers of that. Basic analysis. And the truth is the author of the doing basic analysis. The one with carbon, with a lot of salt on the carbon plate. I also use that book as a reference for this class. Okay, so they are all these people are pioneers of this subject. Okay, so the textbook also decides that they prefer we will prefer this to be informative type. So it's not exactly non-informative. Okay, but it's really informative. Meaning, well, we have a little bit, it contains a little bit information we have it, but not too much, because we still want the data to go. Okay. The main problem is the author knows something about the value of the file that we pay. Okay. So in that case, we want to restrict the parameters. Sometimes right, it has to be obvious, and there's no approximate range of a certain value. Okay. So all these can be sort of put together in the file. Okay. So in such cases, we will do file to some good information in Taiwan without being afraid of being simply the file is working. The good prior information to define those problems. Okay. Important prior are very strong prior that convey a lot of information. But depending on the problem, it could be easy or not to find this type of prior. I mean, basically, remember I told you at the beginning of this class that this spatial validation is used, I mean, very often in many fields, medical, or social science, or statistics field. Okay, those people, okay, or chemical students, okay, they use spatial analysis. So they may already have a good understanding of a certain problem. Okay. For example, if you are a medical expert, you have some experience on certain medicine for a long time. So from your prior experience, you should know certain problems very well. Okay. And now you should have more data. I'm not saying data is not important, but I'm saying that if you don't put in your knowledge about this problem into this analysis, that's a shame. Okay? I mean, so the way to put in your prior knowledge is through this bias. Okay, so for example, structural bias matter. People have to use the basic, not basic, all the prior information they present to study and the associated predict the structure program. Because they spend years collecting data from so many years for a long, long time. And so the people, the researchers in that area actually already have great amount of prior information. Okay. It's not easy to be a mistake. Okay. It's just building a car. Okay. And you have designing a car. I mean, you need to start from reinvent the engine, reinvent the wheel. This is not very fast, right? And you have to utilize, make use of the prior knowledge to aspect right there. The take-home message is if you have reliable prior information, there's no reason to discuss everything. So, including the non-sensitive argument that the objective the meaning throwing away variables. So don't do that. Okay. You should use bias. You use your information. Okay. Make it like fine. So use how you use it based on your use it fine. Okay. So let's take 10 minutes break. We'll come back. We'll continue on the discussion. Okay.
There was a discussion with department chair downstairs. Okay, so I think okay. The important thing here is as I said, prior is here is an argument for frequentist statistics, okay, some of their results can be considered as a special case, okay, of Bayesian model, okay. So for every model, Bayesian or not, has some kind of prior in one way or another, okay. Here when we say some kind of prior in one way or another, we are referring to certain assumptions. Okay, even if the prior is not set explicitly, we will have certain assumptions there. So many results from frequentist statistics and it can be seen as a special case expansion model under certain circumstances. With, for example, with a flat plier. Okay. For example, one of the important approach, okay, called maximum likelihood estimation, okay, which is proposed in traditional statistics, okay. So this method avoids setting a prior and work just by finding a value of theta that maximizes the likelihood. Okay, so it doesn't have a prior, but it finds a value, okay, the value of the of theta, which maximizes the likelihood. So you see, this is like one important difference between the traditional statistics and the Bayesian analysis, because in this traditional analysis, they came up with one value. But in Bayesian data analysis, we normally come up with distribution. Okay, so this value is usually noted by adding a little hat on top of symbols, something like this, theta hat. Okay, or we say it's a theta MLE, because MLE is an abbreviation of like maximum likelihood estimation. Okay, so theta hat is a point estimate. Okay, as I said, like this is a value, okay, and not a distribution. Okay, it's different from, I mean, the result, I mean, we obtain from the Bayesian analysis. So, okay, I mean, it's not like we cannot get that in the Bayesian data analysis. Okay, for example, for a coin flipping problem, okay, we can compute this analytically. So theta hat is actually y divided by n, the number of heads divided by the total number of trials. Okay, so if you go back to figure slide 101, you will able to check, okay, that the mode of the blue posterior, okay, to which is a uniform prior, okay, agree with the value of theta, okay, computed for each subplot. So this one. Okay, original is blue, right? Okay, so you can see when you have a one trial, one head, so the y divided by n is 1, right? Right? So you can see where you get the mode for the blue distribution. So 1, right? Okay, and okay, when you have two trials with one head, the y divided by n is 0.5, right? So for the uniform prior, okay, what you have, okay, is this one. This one you can see the max value, the mode, happen at 0.5, which is 1/2, right? And let me just, for example, okay, 4 trial, 1 head. So in this case, the theta hat, the estimated MLE will be 1/4, which is 0.25. I mean, you can see that, okay, for blue distribution, the max value happens somewhere here, which is 0.25. Okay, so basically, okay, the MLE, okay, the maximal likelihood estimate, okay, can be done, okay, by the Bayesian analysis. I mean, you just need to assume you are using a flat plier, okay, and the MLE will happen at the mode of your distribution. Okay? Okay. Okay. So okay, it basically like MLE can be considered a special case of Bayesian model, one with a uniform prior. Okay. So there are a lot of like benefits, okay, of using priors. Okay. So we get several benefits. Okay. A distribution of plausible values, and not only the most probable one, because the prior is a distribution, right? I mean, you are not confined by just some possible values. You are actually able to provide like much more complete information for your prior knowledge to this problem, okay, because it's distribution as well. So also we get the transparent models, okay, meaning they are easier to criticize, debug, and hopefully improve, okay, because everything can be seen, okay, from like the analysis. I mean, because posterior is obtained from a prior and the likelihood. And the prior basically contains all the prior knowledge about this problem. So, if you want to, criticize or debug your model, okay, everything will be there. So it's very easy to observe, okay. And also, of course, like building models, okay, is an iterative process. We talked about that previously, right? Remember we explained what the model is, okay, and we explained like how to build them, okay. So sometimes iteration take a few minutes. Sometimes it could take years. So it sometimes involve you, and sometimes involve people you do not even know, okay. So this is like it depends. I mean, remember like we talk about. We didn't have talk about this, but we talk about like a lot of time like you are not the one to collect the data. Remember, I mean, when we talk about data collection, I mean, so a lot of time, I mean, this data analysis is not done by only one person. It's actually a teamwork. Okay, so reproducibility matters, and transparent assumptions in a model contribute to it. This transparent assumption means that, I mean, you pretty much wrap all the assumptions in your prior, okay? So we are free to use more than one prior, okay, for a given analysis if we are not sure about any special one. It's just like, for different prior, we can have different result, okay? For example, just like, what we have here, we have 3 different priors, right? So doing the analysis with different priors, I mean, it's never an issue, okay? It's, of course, I mean, eventually you need to see which one is the more plausible one, okay? So exploring the effect of different priors can also bring variable information to the table, okay? So it is actually encouraged to use different priors, I mean, in the analysis. So part of modeling process is about questioning assumptions. So priors, obviously, I mean, are just, your assumptions, okay? And different assumptions will lead to different models and probably different results, okay? So by using the data and our domain knowledge of the problem, we will be able to compare models, okay? If necessary, decide on a winner. Okay, so the chapter 5 in the textbook actually tells you how to do model comparison. Okay, so of course, like we will get to that point later. Okay, so creating report and communicating results is central to the practice of statistics and data science. Okay, so we will briefly discuss some of the peculiarities of this task when working with spatial models, okay? So we will keep looking at the example in the future, okay, about this important matter. So how do we communicate our analysis with other people, okay? How do we criticize the result, okay? So the first thing, okay, how do we represent the model? Okay, if you want to communicate the results of analysis, you should also communicate model you use. Okay, a common notation to succinctly represent probabilistic model is like this. Okay, theta. Okay, this delta represent is distributed as. Okay, so we know theta is distributed as beta distribution with alpha and beta to be the parameter. Okay, or you can say that beta is drawn from a beta distribution. Okay, with alpha and beta being the parameter. Okay, and then okay, y is distributed as a binomial distribution. Okay, binomial likelihood, you can say that, binomial likelihood, where n is 1, p is theta. Okay, yeah. So this is just an example. Okay, and there's actually visual representation of model, something like this. This is explained in the Kruskal textbook, the Doing Bayesian Data Analysis. Okay, so so obviously, like on the top, you can see the beta distribution. We specify alpha beta as parameter of this distribution. You may argue, well, the beta distribution does not necessarily look like that, right? It doesn't matter. Okay, it's just a we just we just put the beta here. Okay, here we just it's just we just represented the distribution like that. Okay, with alpha beta parameters, and then okay, this delta represent the same meaning. So theta is distributed as that, and then this arrow represent that theta is sampled from the top distribution. Okay, theta is sampled from the top distribution. Okay, and then okay, which will be used in this binomial likelihood, right? This theta will be used in the binomial likelihood. Okay, and n is 1. Okay, is another parameter, and then from this, distribution, you get your y number of heads, which is your data. Okay, so this is you can sort of think of this as like a visualized representation of this approach. Okay, this is a visualized. Which one is better? It's really up to you. But of course, like normally, okay, if you are a more visual person, then probably this is better. Okay, because sometimes like later on you will see that okay, it's normally easier to convert the visualized model into program. Okay, if I remember correctly, it's like converted from the bottom to the top. Okay, but anyway, like we will get to that point later. Okay, when we talk about next chapter. Okay. So on the first level, we have prior that generates the value of theta, then the likelihood, and on that last line of data, y. So arrow indicate a relationship between variables, and the tail dot represent the stochastic nature of the variable. So that's about that figure. Okay. So the result of Bayesian analysis is posterior distribution. So this is very important. Okay. All the information about the parameters given a data set and the model is contained in the posterior, okay, posterior distribution. So by summarizing the posterior, we are summarizing the logical consequences of a model and the data. Okay, so the practice is to report for each parameter the mean, okay, to have, or model, or mode, or median, okay, to have an idea of the location of a distribution, and some measure, such as standard deviation, okay, to have an idea of the dispersion, okay, or the uncertainty of the estimate. Okay, so you see, we need a way to describe the central tendency, where the central tendency is, and we need a way to describe how concentrate, okay, we are to that central tendency. So, I mean, we have described this repeatedly in today's class. Okay, the central tendency is normally represented by mean, the mu, or mode, okay, omega, okay, or median. Okay, we didn't use median earlier, but you get an idea. Okay, and standard deviation, okay, is used to represent like how wide, okay, how uncertain you are to this central tendency. Okay, so the standard deviation work well for normal-like distributions, but okay, if the distribution is not normal-like, what do we do? Okay, for example, it could be skewed. Okay, distribution could be skewed. So an alternative way is to use this one. Okay, we call highest posterior density. Highest posterior density. Okay, another way to call it is highest density interval. Okay, on posterior. Okay, so you know, when you say HPD, okay, of course it must refer to a posterior. Okay, but when you say HDI, it does not necessarily indicate a posterior distribution. But no matter you are talking about HPD or HDI, it must describe a distribution. Okay, it must describe a probability distribution. Okay, so what is this, HPD or HDI? Okay, it is defined. It's defined as the shortest interval containing a given portion of the probability density, which reach a certain percentage. Okay, normally we use 95. It's kind of just like remember like if you are a little bit familiar with like traditional statistics, like we used to talk about like a confidence interval, and in the confidence interval we talk about 95 confidence interval, something similar to that. But what is this? Okay, let me show you some figures. Remember here, when I show you these figures, you see there's a 95% HDI on the figure, right? Remember at that time I told you we will talk about this later on, right? Okay, so these are the highest density interval. Okay, HDI represent the highest density interval. Okay, 95% means like, okay, the shortest interval such that when you integrate, do the integration from here to here, you get a 95% of your distribution. Okay, so practically, how do you find it? It is fairly easy, okay? Because we want the shortest interval, right? Because we want the shortest interval. So the higher the better, right? Because eventually we are doing this integral. We are we want the shortest interval to get the largest area, right? So the idea is like this, okay? You imagine there's a horizontal line, and you just, move that horizontal line down, okay? And for example, here, you move the horizontal line down, it will touch the contour of this distribution at the 2 point, right? Or maybe more than 2, but anyway, you get the idea. So, for example, when we touched here, okay, these two, you just do the integration from here to here, then it will give you a portion of this distribution, right? So as you move this line, this horizontal line down and down, okay, the integration of this range will be larger and larger, right? So at the exact time when this portion reach 95%, that's the interval that you have for this highest density interval. Okay? If I try to explain HDI, intuitively, that's how you get it. But of course, you don't need to do that. You can just write a program to have the computer to get it for you. Okay? I'm not saying you have to, really draw a horizontal line to do this. Okay? And you can see. Remember what I told you? If you're talking about the HDI, it has to refer to distribution, right? Okay, so you can see we draw the HDI on the prior and the posterior. We didn't draw HDI on the likelihood, right? Why not? Because likelihood, remember what we discussed earlier, likelihood is not a distribution. Binomial distribution is a distribution when you use y as like the x-axis. It's a discrete distribution. But if you use theta as a x-axis, it's not considered as a distribution. Okay, and if you use HPD, okay, then HPD can only be used for posterior. So these two are 95% HPD. But you cannot say, oh, that's HPD. No, because that's not a posterior. Okay? Just want you to get an idea. Okay? So this HDI or HPD is another indication on how dispersed or how concentrate, okay, your distribution is to that central tendency. Okay, if your interval is narrower, that means you are more confident that the data is at the center. Okay, something like that. Where are we? Okay. So, yeah. So we normally do 95%, but we could do other percentage as well. Okay. So according to our data model, we think the parameter in question is between 2 and 5, with a probability of 0.95. That's like a 95%, HDI or HPD. So there's nothing special about choosing 95%, 50%, or any other value. Okay, they are just arbitrary, commonly used values. But 95% is the default value. To be honest, I mean, we use 95% the most. Okay, ideally, justifications should be context dependent and not automatic. So remember, I just told you we can use like a package to obtain the posterior and also like to find the HPD for us. Okay, so the RVs is the Python package that can for that we can use for like a Bayesian analysis. And RVs, I mean, one of the function in RVs, which is az dot plot dot posterior. Okay, basically like can draw the posterior for us, and it will also generate the mean and the HPD of the distribution, okay, for us. And this is an example, okay? And you can see the mean is specified as 0.3 here, and the HPD is indicated as from 0.1 to 0.5. But this HPD is 94%. Interestingly, okay, RV's package, the default HPD is 94%. It's not 95%. Don't ask me why, okay? I don't know why, but you could reset this percentage to a different value, okay? The default value is 0.94. So you can change this by passing a different value to this credible interval argument. If you want 0.95, which is what we normally use, okay? So you just pass that argument. With this, pass this value to this with this argument. So highest posterior distribution interval, okay, is not confidence interval. Previously, I just told you, okay, it's kind of like confidence interval, but they are really not the same. They are very different. Confidence interval is used by frequentists, okay? The concept is based on the p-value, okay? And for highest posterior density, or HDI, okay, if you want to say it like that, basically, okay, it's a very, very simple idea, okay, to describe like the most probable interval for distribution. It has no any particular prior assumption, okay, when you obtain this highest posterior density, or HDI, okay. So HDI or HPD are more intuitive and without a lot of assumptions, so it's easier. And then it's the following is a posterior predict check, which is like to verify the model result makes sense, but because I will have like a lunch appointment with like a speaker, so I probably cannot finish this slide. Okay, we still have how many slides? Yeah, I don't think we can finish that. We have like 7 slides left, but we should be able to get it done like maybe like another 15 minutes. So I will finish this up, this chapter, okay, next time, and start a new chapter. In our next week's lecture. Okay. So any question? If no question, that's it for today. Okay, and I will see you in a week then. Okay, thank you. Several concepts, okay, and we talk about the conjugate prior, and we talk about coin flipping example, and how to use RVs and PyMC3, okay, to create a result, okay, and we have this posterior, okay, and but of course this interval indicates the 94% HPD, as I said. Okay, normally we use 95, but this book used 94%. Okay, the reason is because
pi MC3, the D4 is 94% NPD, okay, and by doing so, okay, it leaves like 3% on, roughly 3% on the left, 3% on the right, okay, roughly. I mean, I'm not saying, I mean, because when you create the HPD, it doesn't guarantee like the left-hand side, right-hand side, leftover will be both 3%, but you know, it's roughly to be like that. Okay, so just want you to be aware, and they will indicate a mean. Okay, of course, I mean, all this can be changed. Okay, you can also find the mode. You can find the 95% PD with a different setting. Okay, so. But how do we know? Okay, the result is consistent. Okay, the result is consistent. Okay, when I say the result is consistent, I'm talking about the model that you use is correct, or the way you analyzed is correct. Okay. In Bayesian data analysis, okay, we do it through the posterior predictive check. Okay, so you can consider posterior predictive check as like the way to verify, I mean, what you have done so far is correct or not. Okay, so. We know the posterior is P probability distribution of the theta on the condition of the data, right? So it is denoted as like this. Okay. And the posterior predictive check is to obtain the P, okay, probability distribution of the y hat on condition of given data. So what is y hat? Y hat is your prediction. Okay, y hat is the prediction from the model. Okay, from the model. Okay, so given the data y, okay, how do you calculate the predicted value? Okay, I mean, to be exact, okay, it is done through the two things. Okay, this one, P of theta on condition of y. This one, I mean, we know, I mean, pretty well. Okay, times P of y hat on condition of theta. Okay, the integration of this over the theta. Okay, these two terms, the first one obviously is the posterior distribution, right? Okay, the second one here, you may ask, what is this? This is given the model parameter. Okay, we want to find a distribution of the data point. Okay, we want to predict the distribution of the data point. So it's like, okay, you get the theta from this probability distribution, and then you use that theta to sample y from your model. That's the result of this one. Okay, so you can treat this thing, okay, like posterior predictive distribution. This is a distribution, by the way. Okay, this is a distribution. It's a probability distribution. In other words, okay, when I say it's a distribution, what I infer is like the integral of this. The integral of this is going to be 1, right? Okay, so what I mean here for this formula is that, okay, conceptually, okay, we approximate this integral, as a, it's an iterative 2 steps, okay, as follow, okay. Yeah, it's an average of conditional prediction over the posterior distribution of theta. So this is this actually indicates an average, okay, average over the posterior distribution of theta. Okay, we want to see the predicted value of the y, the data. Okay, so these 2 steps is actually simple. Okay, very simple. I mean, even simpler than we the past work that we have done. Okay, because we first already have the posterior distribution, right? I mean, remember now we are doing the posterior predicted check. So that's when we already have the posterior distribution. So we just randomly sample a certain value of theta from this posterior distribution. You know, just like a regular sample, okay, you can sample any value from a distribution, right? Okay, for example, from a normal distribution, okay, you can sample a value from that, right? Okay, same thing here. Okay, you can sample a value theta from this posterior distribution. Okay, and then that theta can be used in your model. Remember, what is model? The model is the prior and the likelihood, right? Okay, of course now the prior is no longer that important because you already have the posterior, but the likelihood is still valid. Okay, given the model parameter, you can sample the data from the likelihood. Okay, so you can, we feed the value of theta to the likelihood. Okay, and then we obtain a data point. Okay, again, this is through the sampling process. Okay, you just sample it from the sampling distribution or likelihood, I mean, whatever you call it. Okay, so we just repeatedly, doing these 2 steps. Okay, each iteration, it will give us a value of y hat. Okay, so those are the predictions. Okay, this model gives us. Okay, so through this process, this 2-step process, okay, there are 2 uncertainties. Okay, the first one is the parameters uncertainty. Okay, which is captured, which is from the posterior distribution, because you sample a value from your posterior distribution. So that part has an uncertainty. Okay, the second part is from the likelihood. Okay, so that's you can say it's a model uncertainty. Okay, or likelihood uncertainty. So this process, take into these 2 sources of the uncertainty. Okay. And then, remember, through this process, repeating this process, actually, we are able to obtain like y hat, which obviously also contain a number of points or a number of values, and now, this the previous y. Remember, the previous y represent the data, right? So this y hat is our prediction. So I'm not saying they are the same, but I'm saying that they should be sort of consistent, right? Sort of consistent. I'm not saying like they are the same, but they should be, similar in certain aspect, right? So you check, you use this, we can use them to criticize the model by comparing the observed data, okay, and the predicted data. So y and y hat we compare them to see, okay, the differences between these two sets, and this is known as posterior predictive check. Okay. So the goal of the posterior predictive check is to check in statistical term called auto consistency. By the way, you guys, do you know what the meaning? What is the meaning of auto here? If you learn English, long enough, you should know English word consists of certain parts, right? In Chinese we call it 字首字根字尾, right? The root and maybe the prefix and the postfix. Okay, so auto is a commonly used prefix term, prefix for the English vocabulary. Okay, so what is the meaning of this prefix? Huh? Nobody know? Somebody give me some words that start with auto. No, English. Automatic, right? Automatic. Or maybe a motorcycle, right? Okay. Or autonomous, right? Okay. So all these words start from auto, right? So the auto actually implies self. Okay, self. Okay, so for example, when we say automatic, it means that because matic, okay, the matic part is like a kinetic. Okay, it can do something. Okay, so it can do something by itself. So it's what we know. Okay, what we understand the meaning of the automatic. Or motorcycle, okay? The motors, followed by cycle. Cycle, are wheels, right? So the auto means those wheels can run by itself, okay? So that's the meaning of autocycle, okay? So that means auto is a prefix, English prefix, vocabulary prefix for the self. So here, okay, we are checking the self-consistency, okay? These two things, okay, the predicted values, y hat, should be similar, okay, to your data point, okay, y, similar in certain aspect, okay, to a certain aspect, okay? So they should look more or less similar, okay? If this is not the case, okay, there was some problem during the modeling, okay, or some problem feeding the data to the model because, you may have problem collecting the data, right? The data may be biased, okay, or when you collect the data is not prepared correctly. Okay, so that's the problem in addition to the model. Okay, so even in the absence of the mistakes, okay, if you check everything and you don't see any issue, okay, there may still be differences. Okay, we will show you an example. Okay, later. Okay. So trying to understand the mismatch, okay, these differences, okay, could lead us to improve, okay, the model. So we may be able to make the model better, okay, or at least to understand the limitation of the model. Because, remember, model is always a simplification, okay. You can never create a model that capture all the factors. Okay, that's pretty much impossible. Okay, so there are certain limitations. Okay, for the model anyway. Okay, so knowing this issue, okay, of the model, okay, is a very good, variable information. Even if we do not know how to improve the model, okay, by knowing the differences, okay, of the predicted value and the given data, okay, it's still a good, a very variable information, okay. So so we previously we already have this, right? And okay. So we begin our Bayesian journey with a very brief discussion about statistical modeling, probability theory, and the introduction of Bayes' theorem. Okay, so this is basically a summary of what we have discussed. Okay, in this chapter, this is one of the, one of the important chapters. I mean, from the textbook. Okay, so we then use the coin flipping problem. Okay, so as an example, okay, to introduce like the basic idea of the Bayesian modeling. Okay, we talk about how to model the coin flips, and we also talk about how we can use the Bayesian data analysis to do it. Of course, at the beginning, we start by using like those the grid point approach, okay, to compute the posterior, okay. But later on, we also talk about the conjugate prior, okay, which allowed us to analyze the results that without approximation. Okay, we can just do it like analytically. Okay, but of course that means we are restricted to a certain prior. Okay, I mean which is beta distribution, by the way. Okay, for the binomial likelihood. Okay, through those examples, okay, we know, okay, the idea of Bayesian statistics, such as like using probability distribution to build models and represent uncertainties. And then we talk about why the priors, okay, should be used. Okay, I mean we shouldn't be afraid of using the prior. Okay, and we should put the prior on equal footing with other elements as part of the modeling process. Okay, it's just like any other assumptions. Okay, any analysis, any data analysis has assumption. Okay, so the prior is just another assumption that we use for the in the modeling process. Okay, just like a likelihood or like this type of thing. Okay, so we end, okay, by discussing the interpretation and the communication of the result of Bayesian analysis, because like when we have the posterior distribution, okay, how do we interpret the result, and how do we make sure, okay, that result is consistent? Okay, later on we will have a example that goes through this posterior predictive check. Okay, but of course, like because that involves that remember the two-step sampling process, so it is better to be done by program. Okay, which will be the main topic of the next chapter. Okay. So to summarize the work that we have discussed, I mean this chapter, we start from a true distribution. Okay, so this is the true distribution, or like a data that you collect. Okay, and then okay, we try to use we don't know. Sorry, this true distribution is something we don't know. I mean, we only get this. This is the data. We don't know the true distribution. We get this data through the sampling. Okay, just like when you flip the coin, you do not know the real value of theta, right? I mean, somebody give you a coin, okay, or even if you get the coin from the government, okay, you still don't know like the theta of that coin. You can make assumption. You can say, oh, if I get it from the government, it's more likely to be fair. Okay, so it's maybe close to 0.5, right? Theta is maybe it's close to 0.5, but nobody knows the real value, right? So that's what the true distribution is represented. Okay, we don't know the real value, but we can through this we can get certain coin flips. Those are sampled, okay, from this true distribution. Okay, so these are the points, these are the data, and with the data, okay, by constructing a model, okay, I mean which contains the prior, okay, which may not represent, okay, most likely, okay, may not represent the true distribution. It's your assumption, right? And likelihood and prior and the likelihood, the model, okay, these two elements, okay, and combined with the data, you are able to get the posterior distribution, okay, and from the posterior distribution, okay, this represents the parameter of your model, okay, the distribution of the parameter of your model. And then you can sample, value from this model parameter distribution, and then use the likelihood, okay, to sample your predictions, okay. So those are the predictions that you obtain from the posterior distribution, okay. And then, okay, in the posterior predictive check, okay, you check the distribution of your posterior your prediction, and the distribution of your sample data to see what we meant by the auto consistency. Okay, so that's what we are doing. Okay, for the Bayesian data analysis, this is an iterative process, okay, meaning, okay, when you check if there's an inconsistency or if you find somewhere you can improve the model, you need to do it all over again. Okay? Well, so I think I already explained this slide, so I will skip that. Okay? So, remember that the posterior distribution, okay, is a consequence of the model and the data. Okay, in Bayesian analysis, posterior distribution pretty much contains all the information needed, okay, for us. Okay, so any analysis, okay, must be done through the posterior distribution and or like the derivatives from the posterior distribution, okay, which is like for example like posterior predictive check is also something derived from the posterior distribution, right? So one way to evaluate our model is by computing posterior predictive distribution with the finite sample we got in the first place. So this is the posterior distributed check. Okay, notice that posterior distribution is a distribution of the parameters in a model. Okay, and the posterior predictive distribution. These two terms are different. Posterior distribution is a distribution. Yes, that's like the distribution of the parameters, model parameters, okay, on condition on the given data, of course, okay, or like observed like the samples. It's pretty much the same as the data, okay. And the posterior predictive distribution is a distribution of the predictive values, predictive samples, okay, which is averaged over the posterior distribution, okay. Why do I say it's average over posterior distribution? It's because, remember this formula, this one, okay, when you multiply a probability distribution and do an integral, okay, that normally means that you are average over certain thing, okay, that's the, what you are average on, okay? So, okay, this posterior predicted distribution is also a distribution, okay, it's also a distribution. Keep in mind, okay? So process modeling, model validation, okay, is of crucial importance, okay? Not because we want to make sure we have the right model, actually, okay? It is because we know we almost never have the right model. That's very interesting, okay? We actually never have the right model, okay? Why we never have the right model? Because as I already told you, the model is a simplification of a process, okay? So no model is able to capture all the considerations, all the factors that affect the result. So, well, that's why, we almost never have the right model, okay? A lot of time, you simplify the process, okay? And the simplification will make your model, okay, slightly incorrect anyway, okay? And which is demonstrated by the differences between the predicted sample and the observed sample, okay? So we check model to evaluate whether they are useful enough, okay, in a specific context, okay? So keep in mind this, okay, specific context. Okay, after all, everything you analyzed through this model will be used in a certain domain. Either it will be used in the medical domain, it will be used in like insurance domain, it will be used in certain domain. So, when I say useful enough, okay, this term, okay, this model, the results, okay, are really useful or not, okay, is actually, okay, will be determined by, a domain, okay, expert, actually, okay. So, and if not, okay, to gain insight into how to improve them, okay. As I said, we may, improve the model, okay, or something like that, okay. Eventually, okay, there's still differences between the predicted sample and the observed sample, but if the predicted sample already represent enough, aspect, okay, then we accept the model actually, okay. So the last slide, okay, in this chapter, okay, I would like to, talk a little bit about why Bayesian inference can be difficult, okay, because, Bayesian analysis, okay, Bayesian Bayes theorem, okay, Bayes theorem, if you check the literature, it was like invented a long time ago, okay, more than 100 years ago, okay, obviously by a guy named Bayes, okay. If you check out the literature, you will find that actually the Bayes theorem was published before that guy, okay, who is actually a missioner, okay. In the old days, okay, if you want to do mathematics, okay, you can only stay in school or, in the church. Why? Okay. At school, I mean, no question about that. I mean, being a professor, I mean, our job is to do research, right? So you can do mathematics research without any problem, okay? But why I say like other than school is church, okay? It's because, okay, a lot of pure mathematics research almost has nothing to do with with real application. At least like when they were invented, okay, at the first place, nobody considered it's their like real world applications. Okay, so in other words, I mean, in some sense, you can say pure mathematics is a game. Okay, a game. Okay, built on certain assumptions. You derive a lot of stuff, okay, from the assumptions. I mean, you can say it's a mind game, okay, if you want to say that, something like that. That's pretty much, okay, about that. So nobody, okay, I mean, because it's a game, right? So other than like a school, professors, okay, I mean, nobody will pay you, okay, to do like a mind game, right? So if you want to, I mean, be a good mathematician, okay, especially pure mathematics, the second job, the second best job is to work for church, because in church, okay, when you serve the God, okay, other than the regular jobs, I mean, most of the time you are free, right? You have your own time, right? I mean, in church, the missionary, I mean, other than because obviously, I mean, in a Sunday they will be very busy because they are holding certain church, religious events. But other than Sunday, okay, they actually have a lot of personal free time. So I mean, if you look at a mathematics development in the old days, obviously a lot of work was done by professors. Okay, but there are also a lot of important concept being invented by those people in church. Okay, and the base, okay, is a guy serving a church, and he developed the Bayes theorem, and then he actually he actually didn't think. My guess is he didn't think this result is important because he didn't publish this one. Okay, he just before his death, okay, he had just wrote this idea, okay, in his own notes. But after his death, because remember, he's a guy who is interested in mathematics, right? So he has friends, okay, professors, mathematics professors. So his friends, because he's dead, so his friend, basically sort out things he left. His friend accidentally found the notes, and in the notes, there's the derivation of Bayes theorem, and the mathematician, okay, knows the importance of this idea. So it's that mathematician who really wrote the paper on the Bayes theorem, okay, and published that paper, okay. So actually, Bayes theorem was not published by that guy named Bayes, but by his friend after his death, okay. But this has a very important consequence. But this was happened more than 100 years ago. I think it's like a late 1800, okay, late 1800. So it was invented a long time ago, okay. So you may ask, so if you know it is important, why why we don't have base data analysis, okay, you know, in the old days. Remember I told you like a statistics field is like dominated by frequentists, right? Until like a recent 20, 30 years, okay, statistics, I mean, was dominated by frequentists. Why not Bayesian data analysis? Okay, it is because, okay, determining the posterior distribution is difficult. Okay, remember like when you do the Bayesian inference, okay, Bayesian analysis, remember, I mean, from the prior and the likelihood, okay, you are using the data to derive your posterior, and there's an evidence term, okay, which is actually very difficult to obtain, okay, because we are doing, oops. We are trying to derive. Do we have this is what we are trying to derive, right? Like given the data, okay, we want to find the distribution of your model parameter, right? That's the posterior, right? So this thing is going to be what? Remember? Sorry. P of D, okay, and this is P of D on theta times P of theta. This is the prior. This is your likelihood. Okay, when you have a model, okay, it's not difficult to have, I mean, to obtain the likelihood, okay? And the prior is from your assumption, right? So the numerator terms are easy to obtain. The issue is denominator. I keep telling you about that, right? We call this term evidence, okay? And this evidence, okay, in real-world application, okay, it is usually represented by the integral, okay, integral. And this integral, okay, the base rule involve computing the evidence, which is the denominator part, okay, and or marginal likelihood. I mean, this is one of the marginal likelihood, obviously. So the integral for the continuous case, okay, is difficult, okay, generally difficult, okay, unless you are using spatial prior, okay, like conjugate prior. Otherwise, okay, it's difficult, okay. Another way to do it is to use the variational approximation, which will not be covered in this class, okay. If you are in mathematics department or statistics department, they may teach you the variational approximation. But anyway, okay, those are ways to get around with like this integration, okay, the evidence part, okay. And we already talked about numerical approximation, right? I mean, basically, I mean, we use the grid points. Okay, we can use a grid point to approximate this integral, okay? So we basically, cover a space with grid of points and compute the integral by, summing across the points in the grid, okay? So this is like, this can be done, and I have shown you examples. But, okay, it will be a problem when the parameter space is large, okay? Especially when the dimension is high, okay, which is usually the case, okay. The joint parameter space, okay, if it involves the combinations of parameter values, okay, maybe even 10 parameters, 20 parameters, you know, I mean, even if you only sample like 10 points from each dimension, it's going to be huge, okay? So this issue can be resolved by randomly sampling from the posterior distribution. So this random sampling technique called Markov chain Monte Carlo method, okay, actually was derived like less than 50 years. I think it's like about 30, 40 years ago, okay, by a student named Metropolis and his advisor. Actually, his advisor has more contribution. But anyway, okay, that's the beginning of this, you know, MC method. Okay, so this through this, you know, random sampling, you know, technique. Okay, we are able to, you know, efficiently draw the, you know, enough sample points from this, you know, this point space, the parameter space, okay, to obtain our evidence, okay, efficiently. Of course, still through computer, okay, you know, simulation, okay. Otherwise, I mean, if you, I mean, so basically, okay, the prosperous of Bayesian inference, okay, is caused by two factors. The first one is this MC method gets developed, okay, like just you can say recently because you know how long the mathematics like history is, okay. So recent 30, 40 years is really a short history, okay, for this method, okay. And the second thing is because the widespread of the personal computers, okay. I mean, you don't need a GPU card, okay, to do the Bayesian inference, okay. Of course, like you know, if you are able to do the parallel, like processing, okay, it may help. I mean, speed up the Bayesian inference, but it's not necessary. It's not necessary. Okay, just a regular personal computer can do the job pretty well. Okay, this is also one advantage over like some like more sophisticated approach in deep learning. Okay, because deep learning, I mean, if you want to do certain inference, most of the time you need the power of GPU, right? So, but Bayesian data analysis normally do not. Okay, so just want to give you an idea. Okay, why the Bayesian data analysis, I mean, become popular so late, okay, even though the Bayes theorem was invented such a long time ago, okay. So that's about it for the this chapter, and we'll move on to the next one. One moment. So before I move on to the next chapter, okay, as I said, I mean, this chapter, the next chapter involved like, you know, using the program to solve this Bayesian data analysis, and here. So next chapter, the name of next chapter is called Programming Probabilistically. Okay. Oh, by the way, in the past, probably you have like been more you are more familiar with like you know, deterministic programs. Okay. You don't normally do probabilistic programming, but the Bayesian programming, okay, the Bayesian inference programming is inherently probabilistic. Okay, so just want you to understand, okay? This is a topic of our next chapter, and I plan to, we will, today is, well, it's almost, 15 minutes. So let's take 10 minutes break, but before that, I want to tell you, okay, we will probably cover like maybe 20, 30 slides today of this chapter, but I plan to assign the second homework, okay, before the next lecture, okay? So please, find some time to check out the second homework before the next week, okay? So let's take 10 minutes break. When we come back, we'll discuss, this chapter.